will be made available to you. Yeah, so be aware. I don't know when Professor Singh is going to distribute it, but at least you can. All the material will be made available for you to be used further on. Um, I'm sure you are aware of these 17 goals for a sustainable development. Yeah, they have been developed by the United Nations, where all the global countries work together, and they have identified 17 different areas that are relevant for sustainable development. Yeah, because sustainability is a very broad area, yeah, covering many different aspects, and at least this is the basic and the most principal goals and framework conditions for our um, future sustainable for future development, and of course it should be sustainable. And when we come really to the area of sustainability, of course we have to make sure that all our products and services they're really sustainable. And sustainable can only be judged if you look on the whole value chain, if you really look on the whole life cycle of all the different products. It's very important. You start with the production, the use phase, and the end of life phase. It's like a life of a human being. You are born, you live, and finally you die. And that is at least also valid for all technical systems and services. And most of these sustainability goals you've seen before are somehow part of the sustainability, which normally has three main pillars for sustainability. Of course, one is dealing with the environment. This is one key thing. The second thing is, I say sometimes it's about money, it's about the economy. Yeah? So even also the economy, the economic development is somehow relevant, yeah, to be sustainable, to do that. And the third thing is the society. Yeah? It's really how people live, how they interact, which the system you have. And so at least the society is also part of this overall sustainability. Sometimes they have a fourth pillar in this sustainability. It's called the governmental pillar. Um, it's more a question. I would say this is, for me, it's part of this society pillar, how to organize societies, which regulations you are established, and how you at least live together. And at least on one hand, we have nature, we have the resources and the raw materials you find in nature. So all the activities we are considering with life cycle assessment, they always start in nature. Yeah, that's very important. We always start in nature because this is the principal thing where we get raw materials from, where we get energy from. And on the other hand, through the different production processes, finally you can provide product and services. And the overall system, of course, should be sustainable. In the following, or in my lectures, my focus is really on the environmental part of this sustainability. Yeah? So it's really about the environmental assessment of the different technology with a special focus to biofuels. Of course, they have to fulfill economic criteria and social criteria, but my key focus is really on the environment. And when you do a sustainability assessment, at least the overall framework, if you are considering economic or social effects, at least the overall system is always the life cycle analysis, the production, the use, and the end of life. And if you do so, at least you can identify specific indicators that makes it possible to somehow measure sustainability. It's about greenhouse gases, it's about primary energy, it's about land occupation, so how much land do you need. So at least you have specific indicators for specific areas. And there is not an overall one single number that measures sustainability. That is never not possible. If you have so many different aspects in sustainability, you cannot upgrade them to only one single number. So at least you always have to deal with many different indicators, and some of them are more robust than others. Yeah? And this is also part of my lecture to highlight those where we say the scientific basis is quite well. You can really do a good quantification, and it's a useful indicator. And on the other hand, I will also mention some indicators that are not easy to quantify. That's so it really, and therefore it's also important. Sustainability cannot measure it in one indicator. You have many different indicators, so you also need, beside this technical information on indicators, in parallel you always have to talk to people to discuss about setting priorities. What is your key interest? What is your key focus? What is your key need? Yeah, and this is more a process of interacting with people, and in combination with scientific indicators that give you a basic information about the different systems, you have the possibility to make the right decision towards more sustainability. Um, what are two um, I come from Austria, from Europe, and we in Europe are very much focusing currently on two key aspects of sustainability, which include at least many different sub aspects. But one is really the global warming, yeah, that we have an increase of the global temperature. I also heard here that here at university the winter is getting warmer and warmer. Yeah, and it's the same in Austria. We have less snow in winter because it's really an increasing of the temperature observed, which is due to global warming emissions. And the key element here is really to limit the temperature increase by the end of this century, maybe by 1.5, 2 degrees, 3 degrees. Everything more even makes more trouble in adopting the planet to increasing temperature. And this is a key driver also for life cycle assessment, for sustainable energy, to really reduce greenhouse gases. Finally, they should be reduced totally. So this is one key challenge we are facing. And the other one is about circularity. And circularity means we're extracting so much raw material in different kinds of raw materials, not only raw oil, it's minerals, so water, so many things. And of course, the more we use these materials, the longer the lifetime of these materials. That is in favor for sustainability. And of course, we should create less waste as possible. So the more we really can close material cycle in a so-called circular economy, of course, this is also a key pillar. Also in Europe, we have this big Green Deal focusing mainly on these two aspects, beside others, but these are the key aspect: circularity and limiting global warming. And this is a typical picture you find, for example, in documents from the European Commission. But if you look on this concept of circularity and you have a technical background, so to say, this is not a real symbol for circularity, because if in this circle still materials go in and materials are coming out, even this graph is not circular. At least a 100% circular economy is really 100% closed cycle of all the materials. And that is finally what we see in nature. In nature, you find no waste. Yeah, we had the opportunity yesterday to visit a farm nearby, as a small farm, and on that farm they have no waste because they harvest and leave back the leaves and bring back the organic residues. Yeah, so this in nature we see how a closed cycle work, and this is the main idea we also want to transfer to our technical system, to our technical world. Yeah, that all of the materials we have around, that we are really able to use them as long as much as possible, and finally to reuse it for other purposes or for the same purpose. So this is the principle of, of circularity. And on the very beginning, of course, you have to consider what are the key drivers for creating more and more greenhouse gas emissions that are mainly influencing sustainability. And you can apply this formula to different, here it's applied to greenhouse gases, but you can also apply it to water consumption or raw oil consumption. But at least there are four main factors that are influencing the overall greenhouse gas emissions. And I will explain them to you, because the total product of these four factors is the tons of CO2 equivalent. The equivalent is the sum of all greenhouse gases we have. Yeah, it's not only the CO2 from fossil energy, it's also methane, NGO, and many other substances contributing to global warming, But of course, the CO2 is the most relevant one so far, but at least they are summarized as CO2 equivalent. And these four factors, the first factor is an emission factor. Yeah? It tells you how much greenhouse gas emission per unit of energy do you create. Yeah? For example, if you burn 1 liter of gasoline, you create 3 liters of CO2, but you also get a 10 kilowatt hour of energy. Yeah? So it's how much greenhouse gases per unit of energy. This is the emission factor. And of course, the more we have renewable energy, the lower these emissions become. We will see they will not be zero, but they might become close to zero. This is the important thing, yeah? But at least this is the emission factor depending on the kind of energy you use that gives you the greenhouse gas emissions per energy. The second thing is how much energy do you need for a specific service? The service can be the preparation of a dinner or a lunch. The service can also be to lighten up or cool or heat this room here. Yeah? But how much energy do you need? Yeah? And depending on the room, depending on the circumstances, you have the same room, but you need more or less energy for a good cool or temperate, good temperature here. So it's a factor describing the energy efficiency. Yeah? And of course, the less energy you need for the same service, the better it is. And if you have a smaller car, you need less energy per kilometer compared to a bigger car. This is relatively easy to understand. But energy efficiency is really, really very important to really be as energy efficient as possible. The third factor is also relevant. How much services do you need, you personally need? Yeah. How um, I start again with an example from eating. Yeah? How much do you eat? Where do you live? How big is your car? What is your personal need? So really, how many services you need per person, that is also influencing the overall effects. And the very last one is you have to multiply it with the number of persons. And multiply numbers of persons, service per person, energy per service, and greenhouse gas emissions per energy, at least you end up with the overall tons of CO2 per year, per country, per whatever, per capita. Yeah? And this describes the key drivers making greenhouse gas emissions. And this is also describing the main area. That's why I like this formula personally very much, because it describes exactly the type of research my colleagues and me we are doing at the institutes, because we have technical people at our institute. They are dealing with the energy efficiency and they are dealing with the emissions from energy supply. Yeah? Because this is really describing the energy system, at least describing a future energy system. And this is a technical issue. Yeah, so you need technical people working on more efficient systems or more systems using renewable energy. The other two ones is about, at least it's about the lifestyle. Yeah, so what is the kind of life you're living? Of course, you see here in India, you have a different lifestyle than we have in Austria or the people in the US have. So everybody has a very specific kind of lifestyle. Yeah, and at least you might say, last thing we want to do is we all want to have a good life and a happy life, and the surrounding can be at least quite different. Yeah, so it's also about having a good life, and you might have a good life with more or less energy and more or less greenhouse gas emissions. Yeah, so there is an interaction between lifestyle and the energy system, and that's why our research group is called Future Energy Systems and Lifestyle. Because for the lifestyle, this is not an issue for a technical guy like me, not for the engineer. It's for people with a social background, yeah, and describing lifestyle of people. And finally, we think if we really want to reduce greenhouse gases, we have to work at least on three of these factors, maybe also on fourth, but at least on three of these factors we have to work, because they have to go down. And one key issue is the number of persons. Yeah, and it's not only about a big country like India is. I can tell you, I come from the city of Graz. We have 250,000 inhabitants. But people like to live in Graz. So year by year, more and more people are coming to Graz and living in Graz. So on the end of the year, if we make a balance over the emissions in Graz, we should not wonder that we have more emissions than in last year, even if they have the same lifestyle, so to say, and the energy system is the same. But if we have 5,000 inhabitants more on the end of the year, we could not wonder that we have more emissions if you only look on the city of Graz. Um, of course, it's about service per person, energy service, and about greenhouse gas emissions per energy. The nice thing on this formula is if one of these four factors is really zero, then the overall product is zero, then we have solved the problem. Yeah. So do you have an idea which of these factors might become zero, yeah, and might really have a strong effect to decarbonization? Pardon? Yes, they can all. Service per person can be reduced, yeah, yeah, but not to zero because you need food, you need a house, you need a place to work here, yeah, yeah, yeah. Yeah, that exactly. It's the emission factor. So if we really have an energy system that has no greenhouse gases, really zero emission, but you still get energy out of it, then it might solve the problem. But as soon as you start doing a life cycle assessment on any energy system, you see it's never zero. It can be reduced. It can be reduced significantly, but it will never be zero due to natural law, I would say. However, yeah, so that means we have to work on all three factors quite a lot, yeah, because when you multiply them, of course, to that then you see, and the total product must become smaller. And I give you an example from Austria how difficult it is to really reduce um, the emissions. Um, I'm not showing you so many formulas in my lecture. I think on the beginning it's the most complex formulas on the beginning, but at least it's at least a little bit the comparison. On one hand, you have a technology development, and on the other hand, you have the energy demand. Yeah? And the energy megajoule per year you need, if you're in the transport sector, it depends on how much megajoules do you need to drive a car for 1 kilometer. Yeah, that's technology. That's depending on the car. And secondly, you have to multiply it. How many kilometers per year are you driving? So these are two different things. Yeah? The first one is the technical one, energy per kilometer. And the other one is, let's call it lifestyle. How many kilometers per year do you drive that car? Yeah, and when you multiply that, then you get the energy demand per year. Yeah? And if you look here on the graphs here, this is the Austrian transportation sector, the energy demand in Austria in the last 20 years, so to say, and we start in the year 2005 just with an index of 100. Yeah? And you see here the green line tells you that the vehicle energy demand of the average Austrian vehicle roughly decreased by a 10% in the last 20 years. This is not very much, I would say 10% in 20 years. But anyway, we see that the new cars need less energy. Because I studied mechanical engineer, and 99% of my colleagues, they went to the automotive industry. Because that's a typical activity for mechanical engineer, at least in the Central Europe. And when I meet them, they always tell me, we are making so much more efficient vehicles. And then I can tell them it's true. The vehicles you build today, they're really more energy efficient than vehicles we had in the past. But the most important is the red line. How much vehicle kilometers per year did these cars drive? Yeah? And we see in Austria we have an increasing car fleet. So we have more cars this year than we had in the past, is one effect. And second effect is um, people have a car and drive more kilometers year by year due to many, many things, so to say. Yeah? So if we have more kilometers driving per year, yeah, this is the lifestyle effect. And we're interested in product. How much energy per year do we really have? So we have to multiply the red and the green light, yeah. And you see that the energy demand in the past still increased significantly, even we have an improvement in energy efficiency. Yeah, and this is at least the two things you have to consider. There's always a technical component, which is developed by the engineers, and the other thing is really a lifestyle, how people use a certain technology, and then you end up with a real effect in energy consumption or in greenhouse gas emissions. And so the good message is we see everywhere that energy efficiency is increasing due to technology development and its implementation. Because if you have only good technology in laboratory, it doesn't help. You really have to bring it in the economy. And at least the other thing is, the second positive message is this curve also gives you a possibility to reduce greenhouse gases. Yeah? Um, because when you say that the driving the kilometers per year has such a strong effect, yeah, so if you put an effort on reducing the amount of driven kilometers, you can also reduce greenhouse gases. Yeah, and this is of course a big question: is this possible or not? But this formula gives you the possibility. And sometimes, if I make a joke, I tell the people in the Corona time, we also had forced to, to, to stop certain activities. Yeah, and we have very strong greenhouse gas reduction targets. We in Europe, we want to reduce greenhouse gases by 2030, which is in 5 years, by 55%, referring to 2005, which is really a strong decrease. In Austria, we want to have no greenhouse gases in 2040, which is even very ambitious. But if you think on these goals, if we stop driving our vehicles in July, yeah, that means we only drive 50% of the annual mileages. Yeah, if we stop driving in July, we can reduce greenhouse gas emissions by 50%. This is on one hand a joke, on the other hand, just also an example on different measures outside of technology which are also relevant to do that. Yeah. You have a question? No. Okay, so in our research, of course, we have a strong focus on research because we think people are in the focus of everything. Yeah, it's all about us, and it's about our daily need. Yeah, so what do we need daily? You see that on the graph here. Of course, the housing, we need to live somewhere. Yeah, uh, we need to eat something. We need the food. Yeah, we need. It's called consumption. We like to go shopping. We just talked before the good possibilities of going shopping also here in India. Yeah? It's about information. Yeah. So if you come here today, it's about information. Yeah. I bring some information and you can get some information. So we have a need on information to come here. You need mobility. So this is a principal a need. It's also a little bit about recreation. You know, I come from Austria. We like skiing. So you see some skiing here, but people have different activities in their free time. But these are more or less covering all the different areas, all the different needs we have. Yeah, and at least question. Yeah, and yesterday we visited a small village. I point out over there. Yeah, and in that village. They have everything, most of the things they really need, they have in the village. They can buy everything, they have most of the things. So of course, they have to go. You always have to go somewhere. If you don't have the thing you need here, you don't have it. If you want some water and I don't have water in the room, I have to go somewhere. Yeah. Of course, mobility starts when you need something you don't have at the place you are. But it's a question: how long do I have to go for a glass of water? Yeah. Where's the next possibility to get water? Yeah. And of course, if you have small areas where you have most of the things available, of course you don't have to move so far. Yeah? And the second question is, okay, how can I go there? Yeah? If I need a glass of water, I normally can walk there, hopefully. Yeah? But for information, of course, to come here, maybe you have a longer distance. Maybe it's too long to walk. I had to fly here because for walking it was too far. So it's really a question: which possibilities do I have to fulfill my need for mobility? And finally, how do I decide? It's also a question of possibilities. It's a question of money. When it is at least, but this is the way where mobility really starts. That's for us why it's so important to start really with the lifestyle, to ask the right questions, and then we come to the technical system providing you these different services. And in our research, we have many research questions on at least sustainable lifestyle, on low carbon lifestyle. And this colorful picture just gives an impression lifestyles can be so different. Uh, the way you live, what you like to eat, where you go for holiday, what are your interests. But at least we have four key questions in our research we ask all the time. The first question is, who are we talking about? Is it young? Is it old? Is it rich? Is it not so rich? What about this education? Which kind of education people have? So that starts where people have different lifestyle because they have a different background, even in which country you live. So this is the first question: who are we talking about? Um, the next question is how much do these people need? Yeah, what is the daily need for mobility, for food, and for their activities? And what is their way? The third question is what do they consume? Here, for example, we've seen you have much vegetarian food or only vegetarian food. Yeah. So this is a clear, you have vegetarian food. This answers the question what? Yeah. We in Austria tend to eat much more meat. Yeah. So it's really also a question, you're hungry, you want to eat something. Yeah. The question is how much you eat is one question, but also what do you eat? Yeah. And we all know that the vegetarians, in overall, they have a much better greenhouse gas balance than the so-called meat eaters, yeah, because producing meat makes much more emissions, yeah, and this is at least a question of lifestyle, yeah, and and the last question is the most complicated one. Why are people so different? You cannot answer that simply, yeah. But it's part of our research to really understand different lifestyles and to really address people with specific measures that have the possibility to reduce finally greenhouse gases. Yeah, this is at least what we address, and these are the four key questions on sustainable lifestyle. And I would say only two of them, how much and what are the technical questions. Yeah? How much energy do you need and where is this energy coming from? Whereas the other two questions are more for the social people with a social background and describing the society. Coming back to Austria, to the greenhouse gas emission we have in Austria. Yeah? These are the greenhouse gas emissions per year, per capita we have in Austria. Yeah? And you see on the y-axis, I have some German slides because I also want to give you a little bit of a German lecture within, but I will explain. So on the y-axis, you see the greenhouse gases in tons, greenhouse gas per capita and year. And on the y-axis, you see the 9 provinces we have in Austria. So we have 9 provinces, and the final one is the Austrian total sum. And you see in the different provinces, the first one is Vienna. I think most of you know Vienna. We come from Styria, Steiermark, yeah? And there's Upper and Lower Austria, and the overall Austrian is roughly 9 tons of greenhouse gases per capita. So the average lifestyle in Austria makes per year roughly 9 tons of CO2. But secondly, you see that the people in Vienna, they only have half the emissions. They only have 4 tons. Yeah? We come from Styria, we have even more, we have 9. The ones in Upper Austria, they have 15 tons per capita. So it's 5 times more than in Vienna people in another province have. Yeah? And the big question, could that be? Do people live in Vienna more sustainable or climate friendly than we do in Styria or they do in Upper Austria? Yeah? Because then it would be one possibility. If we all go to Vienna, we would all have low emissions. Yeah? So you see somehow this is tricky. Something must be wrong on this view. Yeah? And this is at least the official greenhouse gas reporting. You find India is doing these reports every country globally has to fulfill these criteria, and they only count the emissions that really occur in a specific area. Yeah, so the emissions you see here, the overall sum is really the physical emissions in Austria or the physical emissions in Styria, yeah, which has at least nothing to do with the lifestyle there. Yeah, and if you look on the colors here, you see the blue one is the industry. Yeah, and you see here Steiermark, Niederösterreich, and Oberösterreich, they have much industry because there we have the heavy industry, mainly the steel industry. And you know, the steel industry makes quite a lot of emissions, but the steel industry has nothing to do with the lifestyle of the people living there. Yeah? Because in Styria, we make railway tracks, yeah? Very efficiently, very good, and everybody has to build more railways. Yeah? But 99% of them are exported. Yeah, because it's really for export. Emissions occur mainly in Austria, but the product is exported. So this has nothing to do with my lifestyle. Yeah. On the other hand, we're importing in Austria many vehicles from abroad because we have no vehicle industry so far. We are importing all the electronics, all the handys, all the computers. They are made here in Asia, yeah, and the batteries here, make the emissions here, but we use them. And at least this is a total different way compared to these national greenhouse gas emissions. So my message from this picture is that these national greenhouse gas emissions per capita become totally obsolete in the global economy. Yeah? Because independent where you make the emissions, it's a question where people use these products and services. Yeah? And this, at least, is one step towards thinking about lifestyle and life cycle assessment. So I give you an example. When you go shopping in Austria in a supermarket, you can spend 10 euros for a product basket like this, but you don't get you get all these products, but not a full product. You only get a little piece of chocolate, a little bit of the bread or the water. The idea is this is a basket from the supermarket which helps us to count the inflation rate. Yeah? So you go shopping each month the same things, and you see if you pay more or less than in the month before or the year before. But it's normalized to a 10 euro basket. Yeah? And we took, in our comparison, we ask ourselves, how much CO2 do you emit by buying these products? Yeah? And we found out when you buy for 10 euro in the supermarket, these products, until they end in the supermarket, in total have 4 kilograms of greenhouse gases emitted. You don't see the greenhouse gas because if you buy a bottle of milk or some potatoes, you don't see the CO2. But in the supply chain, until you can buy it in the supermarket, yeah, there's a whole chain behind that made already emissions. So with this 10 euro, you have a 4 kilogram of CO2. And then you might say, "Pooh, is this much or less?" You have no clue. And this is also later on you see in life cycle assessment, if you have only one number, it's difficult to count, is it much or less? Yeah? So you have to find something to compare it to. You can compare it to driving a vehicle. An average vehicle, if you drive this vehicle for 20 kilometers, you emit exactly you emit 4 kilograms of CO2. Yeah? So you can say, if I drive 10 kilometers to the supermarket, spend 10 euros to buy something, and go back 10 kilometers, you spend with the driving the same amount of greenhouse gases with the shopping you did. Yeah? And this is at least, this is life cycle assessment. Yeah? To give a comparison. And the question of this supermarket chain was, we had no clue in the very beginning how it was. And normally, if I go shopping, even in for the whole family, I spend more than the 10 euros. Yeah, yeah. So at least it might be if I shop for 100 euro, yeah, I have much more emissions created with the type of food I'm buying. Yeah, the more meat and the more milk products I buy, the more emissions I have. The more vegetables, and the more fruits I buy, the lower these emissions are. Yeah? So at least this is just a way of applying a life cycle thinking also in our daily life. And then there's a new answer is what is the real emissions of the average Austrian if you apply a life cycle assessment to all the activities the Austrians do. Yeah, they have the need for mobility, they have the need for food, for infrastructure. Yeah, for example, the universities are part of the infrastructure. The living is the housing. It's information and communication, a little bit of waste, and a big amount is goods. Yeah, my daughters would say this is going shopping. Yeah, yeah. So all the things you buy, the clothing and all the other things are in that. So you see, this is the real greenhouse gas emission of the Austrians. And you see, if you sum that up, it's between 13 and 15 tons of greenhouse gas per capita and per year. We've seen before it was only 8, which was a wrong inventory, but in reality, it's nearly the double amount, where only half of it physically is emitted in Austria. The other half is emitted somewhere in the world. Yeah? Even here in India, things you produce here and export to Austria, yeah, also the Austrians are somehow having part of the emissions here or in other countries. Yeah? And this is at least the real overall greenhouse gas emission as a starting point to develop measures to reduce greenhouse gas emissions. And you see here that the overall, the biggest one is really the goods. Yeah? But the goods also include, of course, all the truck transportation. Yeah? Because all the trucks driving around, they only bring the products we need for daily life. Yeah? So they are counted here in the area that needs to supply the services. It's a mobility. It's 1/4 is mobility. Yeah, that's a typical European average, I would say. Food is at 10%. Yeah, and if you we separated this down to other lifestyles, and then you see you might have if you're vegetarian, you only have 30% of these 11, so it's a 3% would be here. So really, depending on this, is the average food consumption. The main message here is really this consumption-based greenhouse gases really starts with the daily needs of the Austrians supplying you the materials. Okay, coming back, what are the characteristics of a future energy system? So this was about lifestyle, and this is about the energy system, and it has one pillar is, of course, use renewable energy. Renewable energy is wind energy, photovoltaic, hydropower, and biomass. Yeah, these are the main energy carriers you can get from nature, and with a high efficient system, you can provide useful energy and the energy services you need. On the other hand, you also need other factors for this energy. Yeah? So if you once have the energy, you also need a system to use it. For example, if you have electricity, you can put the electricity in your washing machine. So depending on the type of washing machine, how much electricity do you need for a certain energy service? So you also need these other factors. Yeah? And also when you live in a house, depending on the type of house, you might spend more or less energy for heating and cooling. And so this is at least another factor. And the more efficient you're here on the right hand side, the less energy you need on the left hand side. Yeah? And people tend to say we just need to build more wind turbines, more photovoltaics, and everything will be solved. But we also have to think about energy efficiency, about the other elements you need to supply an energy service. And I would say here we have much more possibilities to become more efficient, because the more efficient we are on the right hand side, the less on renewable energy we need on the other side. And why can't we say, if it's renewable, it comes day by day, year by year? Why do we have to be careful about using it? Because we don't have so much. We cannot build so many wind turbines. We can build wind turbines where we have the wind blowing. You can build a hydropower plant where you have a river, but we don't have rivers everywhere. We have sunlight, but not also sunlight not everywhere. Yeah, so we are still limited somehow to the amount of total energy, renewable energy we can really harvest, so to say. Yeah, so we are limited on the left hand side. So we also have to work on the right hand side, and this at least describes the energy system on one hand with a lifestyle, and on the other hand, providing the energy service with a high efficiency based on renewable energy. And one important energy carrier, of course, is biomass. And the nice thing on biomass is that on biomass is that we have so many different types of biomass. Yeah, when you start breakfast in the morning, it's biomass. For lunch, you have biomass. All the food, of course, is biomass. Yeah, but also the straw or the wood you cannot eat is an energy carrier. Also, the dung and the manure can be used as energy carrier. Yeah, we can even use the corn or the rapes or the mustard you have here around. Yeah, you can use the oil for eating, but you can also use it for biodiesel or other purposes. So some of this can be used as food, as feed, and for technical systems, but at least you have so many different types of biomass. And when you apply a life cycle assessment to biomass, you have to be very clear which type of biomass you're really addressing. What is the type of biomass you need for your system? And we know from our we have so many different systems using biomass, but what we know about biomass, there is competition about biomass all the time. Yeah? There's a competition between food and feed. Yeah, the more animals you have, the less feed, or vice versa. Yeah, there's a competition on bioenergy. Even then, if you make heat or heat and electricity or transportation fuel, this is a kind of, of um, of competition, and of course for biomaterials, paper, construction material, chemicals, cotton, rubber, fertilizers. So at least what we see is that we always have a competition on biomass, and so how are we going to handle this competition on biomass? And we had in Europe, also in the US, but more in Europe, a discussion when we talked about biofuel, about maize or corn. I don't know if you call it corn or maize. It's the same. Yeah, we call it more corn, maize, but sometimes they call it corn. But if you have, for example, some corn left, yeah, all the corn you need for food. For example, if you go to the cinema and have popcorn, or if you have already fed all your animals and chicken with corn, but you still have corn left. Yeah? The question is, should you do with that corn? Yeah? On one hand, you can say, I make bioplastic bag, yeah? Because you can make a plastic bag out of this corn, yeah? Which is a chemical process where you use the starch, yeah? To make a plastic, and its plastic bag is made from maize. It's a renewable resource and decomposes naturally. Yeah? You can throw it out of the window, and a few weeks later it might disappear. Yeah? That is one advantage you might have. The others say, I can use the same corn and make an alcohol, make the bioethanol to drive my car. Because there it's made from maize, it's a renewable resource, and it reduces greenhouse gas emissions because it substitutes gasoline. So the big question is for us, what is more sustainable? What is better? Should you make the plastic bag with the same piece of biomass, or should you make bioethanol? Yeah? And it's a long discussion. Yeah? Do you have an idea? What would you prefer? Which one? The bioethanol? Yeah. Why? Yeah, it might be, but not in all the cases. Yeah, yeah. But here you substitute a conventional oil-based plastic, and here you substitute oil-based gasoline. Yeah? But you have a strong background in bioethanol, so you think this is the way forward. Yeah. it's a tricky answer. I found one answer when I was in Canada. When I was in Canada, I found a poster saying corn-fed cars are better for the environment. I don't know if you say in India also to feed cars with corn, but in Canada and North America, they are a little bit less emotional. They just feed the cars with corn. And they say this is good for the environment. Yeah, yeah, like you said, because you have an attitude that feeling that the ethanol is quite good. But from a scientific point of view, is really the question: is this true? Yeah? Can you really find evidence that really the corn being used for ethanol driving a car is better than making plastic? I can tell you from a scientific point of view, it's really tricky. It's really tricky. I'll show you the answer a little bit later. I'll show you another example. What we are discussing is when we see a tree. Yeah, okay, this is a nice tree. Huh? You can leave it there and say it's just nice, just leave it. But you can say, I make pulp and paper. This is not a typical pulp and paper tree, I'm aware, but at least you can make pulp and paper out of wood. You all know. Yeah, yeah. Or you can say, I just burn it for power and heat or preparing food. Is one possibility. Yeah? And the question again is it better to make pulp and paper out of this tree, or is it better to burn? What do you think? Pulp and paper? Yeah, because, but we need, yeah, it's again a tricky question. Yeah? At least we need both. What is important, you have to think a little bit more. Yeah? Because if you look on that tree, at least a more specific question is, which part of the tree do you mean? Because with the branches and the leaves, technically you cannot make pulp and paper. It does not work, but you can burn it. Huh? The branches you can burn and make heat and electricity if you like. So say, maybe some part of this tree is good for pulp and paper, and the remaining part is good for energy. That sounds good because you have one source and can make different things. Yeah, and you can also ask the question: are we talking about today or in future? In future, I put here an electronic device here because we are getting more and more used to electronic equipment. So maybe in future we need bioplastic and renewable electricity because need less pulp and paper. I'm an old guy. I still need some paper here to guide me through my own lecture. Yeah? But in future, maybe we need more bioplastic. Yeah? And more renewable electricity, and maybe less heat also because we have better buildings or other ways of supplying heat and electricity. So it's always important to ask more specific questions. And this is very relevant if you look on life cycle assessment, because you first have to be clear what is the question you're interested in. And you only get then an answer for this question. If you ask a different question, you get a different answer. Yeah? And sometimes people mix it up a little bit, but as scientists or as future scientists, you have to be very exact. What is the question? What is the framework? And this is the answer. Yeah? And so therefore it's very important to think about what is the key question I'm interested and then giving an answer. It's also a question if you address here biodiversity or greenhouse gas emissions or other pollutants. Yeah? So what is your interest? So this really has to be specified. But coming back to what is better, the plastic bag or the bioethanol? And I can tell you, maybe it's um, uh, a bad answer for you, telling you that science cannot answer this question, what is better. Yeah? There is no scientific evidence that the material use of the biomass, which is the plastic bag, has a greater sustainability benefits than the energetic use, than just burn it and drive a car or heat your house, or vice versa. There is no scientific evidence to do so. So so we can finish the lecture today, because if I have no scientific answer on that, why spend a whole year, a whole week here on the LCA and saying you on the very beginning there is no way. There must be a second part of it that gives you another one. But there is an evidence if you use the biomass for energy and material, yeah, they are somehow twins. The energy and the material use, which we call somehow biorefining, I will explain later. This has the potential for large sustainability benefits. So we will see that it's always a combination. If you use biomass, independent which type of biomass, it's always a mixture of energy services and product or material services. This is the inherent properties or characteristic of biomass that you have to keep in mind. And they have together a large sustainability potential. That's also important. That does not mean it's always sustainable if you use that for energy and material. No, it has the potential. And this is what LCA can show you. Is there a potential to reduce greenhouse gases? Is there potential to increase biodiversity? Yeah? This is not happening per se. You have to, it has the potential, and if you do it the right way, you really have the best way to do it. So this is the answer. Plastic bag and bioethanol, you really have to make an overall detailed comparison. Yeah? And with the plastic bag, you always have energy products coming along. Yeah? And with the bioethanol, you produce animal feed as a side product. Yeah? So bioethanol alone cannot be produced. And this means we are talking about a biorefinery. Yeah? And a biorefinery is the same thing as an oil refinery. An oil refinery makes you energy carriers and raw materials for plastics. Yeah? And the biorefinery also gives you an energy component, different energy carriers, and it also gives you a material for bioproducts, for chemicals, for animal feed, for human feed, for fertilizer, and so on. So this is the technical processing. I will also talk in my coming lectures more detailed on biorefinery. But biorefinery really means with biomass, you always have to make a kind of biorefining, because to use the potential of biomass always need to use the different components for the best purposes. So that means we don't have only this competition of biomass, what is used for what. We think that this biorefinery approach really has the possibility to integrate the different products, because we need different products. We need energy, we need materials, we need food, we need feed, and the biorefinery really has at least the potential to provide this. In the last 10 minutes of the lectures, I will zoom in a little bit more on the energy, always a little bit on transportation fuels, and we are talking about renewable transportation fuels, and we need more and more renewable transportation fuels, and at least we have 4 different types of renewable fuels. Of course, biofuels, they can be made from biomass, and we will learn later on also. Oops, I don't touch it anymore. We need biomass. We need sustainable grown biomass. In future, you will see it will maybe also be necessary to really certify if this biomass really follows sustainability criteria coming from forestry, agriculture, and also residue. So this is one source for biofuels. Secondly, it's also you can use electricity for electric cars. Electricity should come or must come from renewable sources to really have significant environmental benefits. If you burn coal to drive a car, that's not our intention. So here you really need renewable energy, at least renewable electricity. You can do the same if you make hydrogen out of electricity and drive a hydrogen car, or vehicle, is also a renewable fuel. And last but not least, these e-fuels. I don't know if there's a discussion also going on here in India about e-fuels. On the next slide, I explain you what these e-fuels are. They are made from renewable electricity and a CO2 source to combine it to a synthetic energy carrier. So these are in principle the four options we have to drive a vehicle, which is not only a passenger car, it's also a ship or an airplane. We have these possibilities to use renewable energy in the transportation sector. Just to explain briefly what are e-fuels, they're called electrofuels because they start with water, with CO2, and renewable electricity. That's the starting point. And you use the electricity first to split the water into hydrogen and oxygen. You need energy there, you know. And with the CO2, you have to use energy to split the carbon from the oxygen. That also needs electricity. And when you have hydrogen and carbon, with a certain, you can create all carbohydrates you like to have. And this is at least what the e-fuels are doing. Then you can end up with a gasoline quality, a diesel quality, methanol, naphtha, methane. You can make everything out of carbon and hydrogen because these are the basic elements, as you know. But you always start with water and with CO2. So all the energy is coming from the electricity. And you need much electricity to split the water and much electricity to split the carbon. And finally, if you use this energy, you burn it in a vehicle and you create again water and CO2 and the transportation service. And in this formula, you can say, okay, it's the water going in the circle, the CO2 going in the circle. And the only thing is we need renewable energy to drive the car. That's what remains. And the rest is in the circle. So that's why it's basically renewable. It's basically circular, so to say. But it's not so energy efficient because you have to split the CO2 and the water. But anyway, it's one possibility that the e-fuels might be an energy carrier in the transportation sector for the future. And that's the reason why on this picture you see an aeroplane, you see a big truck, and you see a ship. I don't know if you see the ship in the back here, but a big container ship might be a typical application for an e-fuel in future, like biofuels do. But this is one segment because you cannot fly an airplane with electricity. You can fly it with biofuels, but not with electricity. So finally, it's a question: what are the best areas for this renewable, the optimum application of these vehicles? They all use renewable energy. And the question is on the x-axis, how far do you want to drive, or how big is your vehicle, and how much you want to drive, and the y-axis is how big is the vehicle. And you know, for battery electric vehicles, if you have a small vehicle with a small driving range, that works with a reasonable size of battery. If the vehicle becomes bigger, it might be an area for applying renewable hydrogen with a fuel cell. Even if the vehicle is getting bigger, this is the area for biofuels. You can also drive a small vehicle on biofuel, but there are other possibilities, but you cannot fly an airplane with battery electric. So at least the biofuels have really, due to their strong energy content per liter or per kilogram, they are very suitable for big vehicles and heavy loading and longer driving range because they're very close to conventional diesel or gasoline. And the e-fuels at least have the same area to be applied. They have the same energy content. But of course, the energy you need to make the e-fuel is much bigger. And it's also a question for the e-fuel where the CO2 is coming from. And at least it must come from the air to be circular. But you know, the concentration of CO2 in the air is too high for global warming. But for technical purposes, it's very difficult to get this 420 parts per million out of it. Technically, you can do it, but you need many cubic meters of air going through your system to get 1 ton of CO2. But only then you're really in a closed circle. And the second possibility is if you take the CO2 from biomass combustion. If you take the CO2, when you burn biomass, you get the carbon out of CO2 in a higher concentration because in the chimney you have 12 to maybe 18% CO2, which is technically much easier to get out. But still the CO2 is then uptaken again by the photosynthesis. So at least this is also a closed cycle. Sometimes e-fuels are discussed with the heavy industry, in the steel industry. Well, they burn coke, but it's, if you take it there, you reduce the emissions from steel production, but the CO2 is still fossil based. So the e-fuel then is not a real e-fuel because it still has that fossil carbon in there. You use it twice, but this is at least very tricky in LCA to apply that, but this is at least not the type of renewable energy carrier I have in mind. In that case, the CO2 really must come from air or from biomass to fulfill the circularity criteria. Coming back, what is the current and the future energy consumption in the transportation sector? You see here from 2020 up to 2050. Today, everything is based in transportation sector to nearly 99% or 98% on fossil energy. And in future, we hope that more and more hydrogen, electricity, and biofuel will come in the transportation sector is one thing. And these are scenarios from the International Energy Agency. And they also hope that the overall energy consumption will decrease due to more efficient vehicles. An electric vehicle is much more efficient because you need less kilowatt hours to drive 1 kilometer, because the electric engine is much more efficient than a combustion engine. This is one reason why the overall energy consumption is going down. This is one perspective why it's so important that you learn about renewable fuels, about biofuels, because we need them in future to make our transportation sector more renewable. And you also see on the right hand graph which are the vehicles we put this energy in. And you see the orange part is at least the passenger cars. This light duty vehicles is a name for passenger cars. So roughly half of the energy is spent globally in passenger cars, and the other half is spent in trucks, ships, and aeroplanes is very less, at least. The aviation sector is, let's say, maybe 5 to 8% is only aviation, so really much is shipping and rail, but half of it is really in the passenger vehicle sector, and that can significantly reduce, because here is a very good area for applying electricity. So the other area for the bigger vehicles is dedicated for the biofuels. So coming to a summary from what I tried to bring you in this first lecture. What about systems perspective for people mobility in the future? It's energy efficiency. Yeah, so we really need energy efficient vehicles, and of course, it's on one hand, it's vegetarian or it's food. Yeah, if you think about walking, but it's also renewable electricity as one pillar for people mobility, and we need different technologies. Yeah, mobility starts, as I told you this morning, when you wake up in the morning and get out of bed. Mobility already starts. Yeah, because in bed you don't normally find breakfast. Yeah, so we need to get up to get the food, but then we have public transportation system. We have bicycles. We have, of course, metro trams, and we have, of course, passenger vehicles. So, in my personal judgment, is that for the passenger vehicles, I would think that the electricity is the most efficient one, and that we put the biofuels and the e-fuels in the airplane and ships. Yeah, but we also need airplane and ships for transportation. So this is at least a perspective in future where we put maybe the best choice of technology with the highest energy efficiency, which is really a key for all different applications. Last but not least, to also address a little bit the mobility behavior and the lifestyle, which is totally different here in India, what we saw yesterday compared to, for example, Austria. Normally in Austria, you see one person in a big car, 2 tons, transporting one person. Here you have a motorcycle transporting 3 or 4 persons. Yeah, so this is a total different way of addressing this issue, and that's why we have developed this green box. It's the green box 2.0, and because with that box, if you put that in your car, you can increase the energy efficiency by a factor 2. There's also a box available 3.0 and 4.0. And the clue behind that is if you put that in a car and you have only one person sitting in the car does not drive. If a second person enters the car, then it starts to drive because then it's half the emission per capita for the same distance. And if you put it in the bus and in the tram, there are always more people. This is much more energy efficient. And this is at least a strong story, very relevant in Austria because all the people using their own car for them alone. And this is on the medium term a big question on changing the lifestyle and make it more sustainable. Same technology, but more people in the same vehicle. Of course, you have more service with less emissions. That's why this green box is one possibility to explain how lifestyle influences this. Finally, this is a summary of the key messages of today. We've seen the key environmental challenges are climate neutrality and circularity. They're really covering most of the environmental aspects. And the future energy system must be based on high energy efficiency. Really use less energy for much service. This is really the key issue. And secondly, the energy must come on medium to long term from renewable energy sources. And we have also seen that the type of the lifestyle is relevant, and this economic development and how many services per people is a key driver for consumption. People drive more if they have more cars and so on. So this is a key drivers. I already showed you a little bit where biofuels from sustainable biomass are part of the solution. They are not the complete solution. Yeah, because for the solution we need many different puzzle elements. Yeah, but of course bioenergy, biomass, biofuel are part of the solution beside others. But we really have to take into account that biomass, the amount of biomass available is somehow limited. There is competition about biomass, but also about land use, which is always coupled with bioenergy. We will discuss later on. Then we've seen that biorefining is at least the technical term how to use the energy properties and the material product of biomass the most efficient way. This is at least the most relevant one. And still the total amount of sustainable biomass is somehow limited due to technical, economic, social, and environmental conditions. Yeah, we will discuss that, I think, the whole week. So the available amount really depends on the circumstances. It's still limited, but it is available in different properties and can fulfill different services and needs our society has. So this is at least the final slide for this first lecture. Um, if you have any additional questions, you can ask them now, or you can ask them during the break.
Good afternoon, sir. Sir, you just mentioned that this formation of different or manufacturing of different fuels and materials from the raw material should not be in competition but in integration. So, can we say that making different products from the same material, it can compensate for the environmental impact that that process is having?
I
Uh,
did.
yes.
Can you ask? I did not get the question completely.
So what I'm saying is that whatever our activity is, let's say we are making biofuels from the biomass or whatever we are making from it, it will have some impact on the environment.
Yeah.
So if we are making multiple products from the same material, can we reduce the impact on environment by doing that?
Yeah. Yes, because when you make a comparison, you make on one hand different products out of biomass, you always have to compare it to something else. So at least you have to compare it, making the products with a different way. For example, driving with gasoline or making the plastic bag out of oil. Yeah. So at least what you do, you compare. If you have different products made from biomass, you have energy, you have a plastic bag, you have food or feed, yeah, and they have a certain emission or influencing biodiversity to a certain degree that you can quantify with some indicators. But secondly, you have to compare it. What would be an alternative way using raw oil for this product? Yeah? And at least in this comparison, then you can say if you have an advantage with your bioenergy system, or you have no advantage, or it's not a significant difference. Yeah? But at least you always have to compare one thing with another thing. And this comparison must be a fair comparison with the same services and for the different indicators. And for example, for this plastic bag versus the ethanol, it might be that if you do a good comparison, that you see that one case is saving more greenhouse gases, but maybe the other case is saving more particle emissions. And it's becoming complicated again. Yeah, you have an advantage here and a disadvantage there. And that we will learn during this week. There are different impact categories and how to judge them and how to handle pros and cons, where you have an advantage, where you have a disadvantage, and what you need to overcome that and to finally decide what to do.
Any more questions?
Good afternoon, sir. Earlier, you said that in Austria, if you don't drive a car for just a month of July, you will reduce the greenhouse gases by 50%. Could you explain that? That's
Yeah, at least one is the technology, and the other one is how you use the technology. Yeah, and we do improvement on the technology, but we also have to limit or regulate or learn how to use this technology the most sustainable way. Yeah? And for example, in where I come from in Graz, in the city center, everything they have due to historic reason many small roads, yeah, and you don't have space for all vehicles there. So we say there in the inner city you have to use public transport to go there, yeah, or the bicycle or walking, yeah. And for longer distances, of course, you can use the train, so it's at least really a mixture of a future mobility system. Is not one technology, at least, yeah. It really has to be adjusted to the need of the people, but also in line with the sustainability criteria. Yeah? And therefore we've seen that it's not only in Austria. It's if we have too many vehicles, we are running out of space to drive them. Yeah, so we really have to rethink our overall system, and this is a big challenge for our society. Yeah, and at least, but we still come back and say, okay, mobility starts when I need something I don't find nearby. So one answer is the more I find nearby, the less I have to go somewhere else. Yeah. And I could have done my lecture here, sitting in my office in Graz, do it via internet. Yeah. That could be one possibility. Yeah. And that is a choice you have to make. I still think it's good to be here to see you and feel you, but you see, there are many possibilities to think about. How can I limit my demand of mobility because I have things nearby? Yeah, for some things you really have to go to. For example, Austria has no sea, so if I want to go swimming in the sea, I have to go to Italy. Yeah, because we don't have the sea. Maybe in future I put up a Google Glass, yeah, and feel like I'm, yeah. However, it's curious, but at least it's something I think we will learn in future, because in the past the energy was available and we have developed the system, and now we see somehow the limits of the sustainability of too many cars or too whatever. So we are further developing in a more sustainable way. Yeah, yeah. I don't know how you see the perspectives here for India. Yeah? It's also and you don't have so many cars per capita like we have. Yeah, so it's you're at a different level, but still it's really a tricky thing to decide on that. Yeah.
Thank you, Professor Ingrid. So, if you have still any questions, so you can note them down, and you can ask them later because we are running for short for the lunch. So we have to start the next session by 2 o'clock. So you can reserve your questions and you can ask later on. Okay. Thank you, Professor Ingrid. So we can now disperse for the lunch, and we will meet at 1:55. Okay.
it's the same one. Yeah. They're all perfect. Yeah. Okay. Welcome in the afternoon. Um, Now the next lecture is an introduction on biofuels, on transportation biofuels, and the question how to come from the different raw materials to something you can use as a for for providing transportation service. So at least we have seen there are so many different types of biomass available, and you have to transform them at least finally to be used in an internal combustion engine. And there's at least a relatively long list of different biofuels. Um, you can use pure vegetable oil in a combustion engine, but in most of the cases you produce a biodiesel by transesterification to fatty ethyl methyl ester, so it's biodiesel. You can also hydrate the vegetable oil to hydrated vegetable oil. It's called HVO. It's an upcoming fuel, not only in Europe but also here in Asia. Then, of course, bioethanol. I think you're quite familiar already with bioethanol. And then there's a long list of different so-called synthetic fuels. At least they all start when you convert the biomass to a carbon and hydrogen molecule, so to say. You're able to recombine it to different different synthetic fuels. And then there is biomethane, mainly coming from biogas production, and then upgrading it to biomethane. So these are the six most relevant fuels relevant today, but also being developed in future. And then there's a still longer list of many other biofuels under development. You can use pyrolysis oil, you can use high temperature fuels, all dedicated for very special feedstocks. At least, but when you look on the list of biofuels, we have two different types of combustion engine. We have the Otto engine and we have the diesel engine, and not all biofuel is suitable for both. At least each biofuel is suitable either for the Otto engine or for the diesel engine. And at least most of the biofuels you will see later on are currently used as blending. So you blend up gasoline, you blend up diesel to E10, E5, or B7 or B20. That's the big commercial use of biofuels today. And you see that it's mainly the the biodiesel, the hydrated vegetable oil, and the so-called Fischer-Tropsch diesel. They are typically, or they can only be used in diesel engines, whereas the bioethanol, the biomethane, they are mainly dedicated to Otto fuel, to an Otto engine. That's the Fischer-Tropsch diesel. I don't know if you heard the name of Fischer-Tropsch before. I will explain later on, but it's a diesel quality, but it's a process where you gasify the biomass, at least to the carbon and hydrogen molecule, and then recombine it to a diesel. And this process was developed in Germany by Mr. Fischer and Mr. Tropsch, and so it's called a Fischer-Tropsch diesel. And this technology was used on the end of Second World War, when they were running out of petrol. They can convert coal to petrol and gasoline. And then traditionally today, this is used also in South Africa still, because they have so much coal there, where they convert the coal to a diesel and gasoline quality. I don't think in India you have this process, but I don't know. But it's at least it was developed by Mr. Fischer and Mr. Tropsch. And it's also at least a possibility to convert solid biomass also to a diesel quality. Forest. Of course, there are two types of forest. Normally, you don't use the big stems, because the big stems are used for furnitures and for other and construction material, but all the leftovers. Yeah, so parts that the bark and the smaller parts and the branches, and also the very thin ones, they are very well dedicated on one hand for the pulp and paper industry, but also for the energy sector. Yeah, so in forestry, you have a possibility. And then in the trade and industry sector, very often biogenic residues occur from different production processes. It could be bark, it could be cooking oil. Yeah, in Europe we are collecting cooking oil quite a lot. Yeah, because if you collect that, you can convert it to biodiesel. And this is at least a biogenic source in the trade and industry sector, which is available. But as it is a residue, it is always coming in an amount depending on the main product they are doing. Yeah? So the more French fries you eat, the more waste cooking oil you come up. Yeah? Or in Austria, we like Wiener Schnitzel. I don't know if you know Wiener Schnitzel. Yeah? You also need oil made meat. Yeah? That's very typical for Austria. And this oil then can be used for biofuels, but it's at least it depends on how many French fries or Wiener Schnitzel you eat. Then you have more, so you cannot increase it because it's just an amount available. And the last thing is this so-called aquaculture. It's mainly about algae and seaweed, but it's mainly algae. They are growing in these artificial systems, these algae, so they are growing in water, and you have to put in, they must be heated and all the fertilizer. And the idea is they do photosynthesis, and they're growing, and they're also containing oil or starch or even sugars. But this is still a developing process. So because all these systems you see here, they still need more energy to operate the system in pumping the water and putting in the nutrients compared the energy you get out. Yeah? So that the relation is not an energy producing system at the moment. But some people hope that the algae, because they have a very high theoretical potential per square meter or per hectare, yeah? Because if you really feed this organism quite well, they have the ability to really grow fast and provide big amounts of biomass, but still they are under development and not yet commercially available. So if you once have the biomass, of course, you have to convert it to an energy carrier. And there are many different conversion processes available. And at least you can separate them in three main groups. One is the biochemical one. So this means a biochemical conversion, which is mainly aerobic, or you can also call it alcohol fermentation. I think you're familiar with that. Or you can do it anaerobically. Yeah. So on one hand, you get an alcohol and an animal feed in most of the cases. In the other case, you use biogas, which is mainly used for wet material. It's manure. It's dung. You can convert into biogas. And you then get an energy carrier, the biogas, but you also get an upgraded fertilizer. So the leftover, the digested material has a very good fertilizing quality because you have a reduced carbon content, and that is very well being applied as a fertilizer in agriculture. So these are the main biochemical conversions. For the alcohol fermentation, I think you always need a sugar, and the sugar can be made directly if you have sugar from sugar beet or sugar cane, or you have to convert starch into sugar. But in future, you can also convert cellulose via enzymes to sugars. So you have a broad spectrum of different raw materials, but still you need a sugar to be fermented. The second group means thermochemical. Thermo means you need temperature, at least temperature and heat, and you see that here in in the middle you put in the biomass, and if we heat it up to 800, 900 degree, the biomass starts to decompose, and first it melts, so first it becomes a liquid, and if you further heat it up, it becomes gaseous, and then you can create at least a product gas. And if you upgrade it further and separate the different particles and also other components, at least ending up with a pure carbon monoxide and hydrogen. So this is called the synthesis gas, which was also the process Mr. Fischer and Mr. Tropsch developed. Because of these two molecules, you're again able to produce all different types of fuels, diesel quality, gasoline quality, but also raw materials for the chemical industry. This is the thermochemical process. And the last is the physical or chemical or even pure mechanical processes. So if you convert the rapeseed to rape oil, you just have to press it and you get the cake and the oil. This is relatively simple. But then converting the oil into biodiesel, this is the transesterification process where you put in some alcohol. Normally it's methanol, and you mix it at a relative low temperature. And then it converts into biodiesel and glycerin. The biodiesel can be used as a replacement for diesel, and the glycerin is a very valuable raw material for the chemical industry, for the pharmaceutical industry. They need glycerin, so this is then really a biogenic-based chemicals being used for other purposes. And at least, as I've mentioned before, all of these processes are core processes in these biorefineries, because you always produce a broader portfolio of different products, and these are the conversion processes. This is a big table. I know this is at least the list of biofuels I've shown you before. This is the list of raw materials, from agriculture, forestry, trade, industry, and aquaculture. And in between, you have these different conversion processes. So you can imagine long list of raw materials, long list of conversion processes, long list of biofuels. And there are many different combinations possible from raw material to a biofuel. So you can have one raw material and make different biofuels, but you can have one biofuel made from different raw materials and vice versa. So there are really many different combinations. So far we have, I would say, about 5 key conversion processes for bioethanol, biodiesel, and hydrated vegetable oil, using oil source, sugar sources, and starch sources. These are the key raw materials today. But the list for future combinations is quite long, and there are many things ongoing in conversion processes to different materials, because the demand for renewable fuels, for biofuels, is quite big. You've seen globally we would need a very high amount. So the more we really can convert with new processes, new raw materials into a liquid or gaseous energy carrier, that is quite good. And this is a very busy table. It at least summarizes a little bit for the different, for biodiesel, bioethanol, biomethane, and synthetic biofuels, highlights the most relevant characteristics and combinations from raw material to a biofuel. And for biodiesel, you always have to start with fat or oil. This is the starting point to do something further on. For bioethanol, you need the sugar coming from sugar directly from starch plants, or also from lignocellulosic plants in future. Whereas biomethane is mainly dedicated for wet or wetter material. Via this anaerobic digestion, you go to the biogas. The biogas is a combination of CO2 and methane, and only the methane is the thing you can use. So if you want to use it in a compressed natural gas car, I've seen you have many cars driving on compressed natural gas. There you have to upgrade the biogas to biomethane, which just means to separate the CO2. So you have to get rid of the CO2, and then you have pure methane, and that can be used as a direct substitute for conventional fossil natural gas. Very relevant is, especially for biodiesel and bioethanol, that the heating value per liter is lower than for gasoline and diesel. The reason is that in the chemical specification of diesel and ethanol, you have still oxygen in it, which is part of the chemistry, but gives you no heating value. So at least this is relevant on one hand on the price, because very often people compare the economics per liter, but if you get less energy for bioethanol, you get 30% less energy compared to gasoline, so you have to be careful if you talk especially on prices, that you maybe it's cheaper per liter, but you also get less energy per liter. And also in other circumstances, in statistics or in applications, you really have to be aware what is the real heating value of the biomass for its specific application. In principle, it's so that a conventional diesel car can use a blending of biodiesel up to 10, maximum 20 volume% of biodiesel. Otherwise, these sophisticated engines don't work properly, because then they make more emissions. If you want really a pure biodiesel engine, you still have to change the engine a little bit. So at least the big application of biodiesel nowadays is really to go in blending, because all of the diesel cars accept the blending up to 10% already, and 10% with this big volume still is a big market to introduce or to use biofuels. For the ethanol, it's quite similar, and most of the cars, the new cars, they all are able to run on E10. That means 10% of ethanol blended, and you need a special vehicle, a so-called flexi-fuel vehicle, which is then able to also use ethanol up to 85%, by modification a little bit of the engine, but a pure bioethanol car is not developed yet. It will work, of course, but it specifically has to be developed. And for the biomethane, it's easy, because the biomethane chemically is the same as natural gas. So if you run your car on natural gas, you can also run it on 100% biomethane. So this is at least the same. This is again showing a similar picture coming from feedstock to different products. This time the products are differentiated between liquids and gaseous. In transportation sector, the liquids are so convenient, because a liquid is so easy to handle. So the gaseous fuel in Austria, for example, we have very less compressed natural gas car, which is not a big market at all. So we mainly drive on liquid fuels. And of course, it always competes a little bit with heat and power, because all of these feedstocks can also be directly used to produce electricity and heat. So this is also a possibility, but we will see later on that in most of these processes on making biofuels, you always produce also a certain amounts of electricity and heat that can also be used in this broader portfolio of biomass conversion. And now I'm going to show you the three most relevant value chains from raw material to a transportation fuel, and the most relevant byproducts, and they're at least summarized in three value chains. We call them value chain because we want to create value out of it, which is of course in one hand energy value, to get energy product as one value, but on the other hand also creating economic value, because all these systems only work in reality if the economy also works, if the costs and the revenues you get and the markets are available. So value chain really means it's also an economic incentive to do that. Otherwise, it's not so easy, or even not possible. So the first value chain is the oil and fat based value chain. So at least they always start with oil and the fat. So oil and fat is, I hope you know the difference. It's at least the same chemical thing. One is liquid at room temperature and the other one is solid, but at least it's the same. And you start with an oil producing plant. So this surrounding here is a good example for an oil producing area. So also this is oil. And this oil in the first step, you go into the pressing, which is a relatively simple process, but a very relevant process because you produce the oil. and the pressed cake is a very good protein content, and you can use that as animal feed, for example. Yeah, so you can produce animal feed co-producing with raw oil. In where I come from in Styria, we like to eat our salad with pumpkin oil. I don't know if you've ever seen that. It's a dark green liquid. It looks a little bit like raw oil, but it's really tasteful because we have the pumpkin seeds and we press them, and the oil is a speciality, and the other fraction is a good animal feed for the animals we are housing. So it's also a good traditionally in our province we have this. So this is also a kind of value oil and fat-based value chain, but it ends at the salad. It ends at the table and not in a tank. What you see here is at least you then get the raw oil, and then the raw oil you need a little bit conditioning and refining to enter two different routes. One route is the transesterification route, where you add at least methanol or ethanol. You mix it at, I think, 60 or 70 degrees, and after a certain time, you get the biodiesel and the glycerin fraction. Yeah, and the glycerin is used as a byproduct, and the other one is the biodiesel or fatty ethyl methyl ester. The biodiesel was the traditional wording of it, but now more and more people talk about FAME or FAME, but it's chemically it's the same. And normally you can do the biodiesel, you can do in small facilities. So the process is at low temperature, at low pressure. So at least it's a relatively simple process. You can really make decentralized units. And this process, I have an additional slide on it. This process was developed in Graz, where I come from. It was in the beginning of the 90s. Where they have developed the chemistry, how to convert vegetable oil to a diesel quality. And then in Graz, they also developed this application I will show you later on. So it's a relatively simple process, so to say. If you see the second process here using hydrogen, for the hydrated vegetable oil, you need this hydrotreatment. So you need the hydrogen to get rid of the oxygen in the vegetable oil, yeah? And this can only be done on a bigger scale. Normally these processes are integrated in an oil refinery because there you have good sources of hydrogen, and with this hydrogen you can make big amounts of this HVO, and there are 2 or 3 big plants globally that really making big amounts of the HVO, and the quality of the HVO is really identically to the diesel because there's no oxygen in there anymore, so the HVO really has a perfect quality. And with the HVO, you can drive a diesel engine by 100%. This is the big advantage. Whereas for the biodiesel, you are limited by the properties because you still have oxygen and other things in there that do not fully be equal to the diesel. And it also has a 10% lower heating value than conventional diesel. Yeah, and you see here, so oil and fat is the starting point. You get 2 transportation fuels, the biodiesel and the hydrated vegetable oil, and you get different byproducts, yeah, from animal feed, but also chemical, pharmaceutical chemicals. The second value chain is the biochemical value chain, and it's called biochemical because the core process of this value chain is the fermentation. So the fermentation is in the center of this value chain, and you always need a sugar to go in there, and at least the raw materials are the sugar crops, the starch crops, and in future and also today on the pilot scale, these lignocellulosic materials, which are the main relevant is really wood and straw as the main big sources of lignocellulosic materials, where the cellulose and the hemicellulose can be converted to sugars, and that works all via enzymes, you know, yeah, like we have in our mouth. These enzymes, they're similar to the ones you need to convert the starch into sugars, and then you have the yeast, and you make the alcohol. A big difference is always the alcohol concentration you get after fermentation from the different feedstocks. And of course, the higher it is, the less water you have to evaporate afterwards to get really 100% alcohol. Yeah? But only the 100% alcohol is applicable to an engine. And so from environmental perspective, as you need a heat source to evaporate all the water, it's always a big question, where is the water, not the water, where is the energy coming from to evaporate the water that influences the balance totally. And the leftovers from the fermentation, of course, that is a very good animal feed in most of the cases, yeah. And you can further upgrade it also to other materials. If you come from lignocellulosic material, the lignin cannot be converted to ethanol, yeah? But the lignin remains on the very end. It can also be a solid fuel, or it can be used as an energy carrier, yeah? It's the same like in pulp and paper industry. They only use the cellulose for the paper, and the lignin is used to provide the energy, electricity and heat to run the pulping process. And of course, when you have the alcohol here, there are different alcohol products and different alcohols being available that can be upgraded on one hand to transportation fuels, but also to other alcohols being used by the chemical industry. So this is the biochemical value chain with the core process, the fermentation, which has at least many possibilities in using biomass for transportation fuels. And the last one is the thermochemical value chain, because the thermochemical processing of biomass is the core process. You find here it's the gasification in the middle, yeah, where you gasify the wood or the lignocellulosic material, but it will be mainly wood or other solid leftovers like kernels, but also straw and others. Sometimes you have to pre-treat the material before you can put it in the gasifier. And in the gasifier, on one hand, you add heat, and on the other hand, you need most of the time oxygen or steam to make the gasification happen, that you have the real chemistry there, to at least to get the product, the raw gas, at least to get the synthesis gas. So the main idea in all this, in this thermochemical conversion, is at least to get again the CO and hydrogen gas, which is a syngas, and that can be further be used to different chemicals, but also different energy carriers. And the difference is only the temperature, the catalyst, and the pressure. Yeah, depending on which pressure, which catalyst and temperature you apply, you can get methane, you can get gasoline, you can get jet fuel, you can get many different products, and it's quite similar what's happening in a conventional oil refinery in the portfolio of processes you get. And this is at least the key reason why this is so relevant, this process, because you can really substitute conventional raw oil products with biomass-based raw materials, and this is at least the key driver for the relevance of this process. So we have at least these three key value chains with specific raw materials and specific final products that are relevant or most relevant in the area of biorefining biomass. This is the picture I wanted to show to you the biodiesel development that happened in Austria in the 1990s. It was developed at university in a laboratory. Yeah, first they tried to do it in a laboratory, and as this was successful, they produced it first liters and tested if you can apply it in a vehicle. Yeah, and this worked very well, and this was a very good cooperation. In Graz we have different universities, and they cooperated on that. And then they found a farmer organization close to Graz where they started to grow rapeseed. Yeah, they grow rapeseed, and they use the animal fat, because animal feed from the pressing, because there were many pig farms around. So this was one advantage, and the oil was then transesterified, and then the diesel was used first only in the tractors in the farms, yeah, and later on, as the volumes became bigger, they also converted the bus fleet in Graz, these green buses, they converted to biodiesel. And as it was such a big success, they were running out of rapeseed, so they also started to collect waste cooking oil, and there was a system introduced in the city of Graz to collect all the waste cooking oil. Yeah? You need a certain logistic. Yeah? You first start with the big producers, but then also go to the households to collect the waste cooking oil. This was a very good source. And finally, it worked that we collected the waste cooking oil in Graz, then converted it nearby and brought the diesel back to feed our bus fleet. Yeah? And this was a very successful activity starting in Graz. And then now we have a big company called BDI. They now produce these biodiesel producing plants globally. Yeah? Because it's, even if the technology is not so sophisticated, you need somebody who is able to do that. And this BDI is now an industrial company building biodiesel plants all over the world. And this is at least a very nice success story from laboratory development via testing, via piloting, finding a pilot area, and then making an industrial and economic success out of this. And this is something we in Graz are really proud of. And I was the first one making a life cycle assessment of this biodiesel being produced. I did it already at university for my master thesis. Yeah. This was the topic to analyze the greenhouse gas balance of making biodiesel. At this time, it was beginning of the 90s, I did my first LCA, and the results are still valid today. Yeah? So my calculation was not so bad, even we know much more today about these processes than we knew in the past, but still the orders of magnitudes on greenhouse gas saving it was, and when you use rapeseed oil, it's roughly 60% less greenhouse gases. If you use waste cooking oil, it's more than 90% greenhouse gas saving, and at least that was also part of my personal activity. Thank you very much. And that was at least really the starting point for me to step into that area. Yeah? And even at university with life cycle assessment, I was some kind of exotic, because nobody did that at technical university before, and they told me, you're a mechanical engineer. And finally, when I made my big examinations with all the professors sitting there, and I presented my work on life cycle assessment of biodiesel and so on, and they were listening and said, that's really interesting what you do, Mr. Jungmeier. This LCA what? LCA, yeah. But we think this is too complicated. And maybe it's better in future you go in a traditional workplace for a mechanical engineer, go to the automotive industry or making power plants, but this LCA, I don't think this will. So this was the recommendation when I left university, but I was so fascinating of this area, and then I had the opportunity to start at Ioneum Research already at this time, and there I really had the possibility to develop this methodology further on with academic cooperation and with industry cooperation, and I had then the opportunity also to make my PhD out of this activity, and this is what was quite nice, and really started with these biodiesel activities we had at the beginning of the 90s in Graz. And today we have in Austria roughly 8, 9, 10% biofuels on the market. Yeah? So we really have introduced them. It happened, the introduction happened in Europe because there was a law by the European Union. They said we need more renewable energy in the transportation sector. This happened 15 years ago. It was a long process. You can imagine if 27, at this time, we were 20, I don't know how many countries we were in Europe, but it took a long time to bring all this country to the same goal, to say we want to have 10% renewable fuels in the year 2020. Yeah, that was at least a political wish, and then it was a political law. It was a regulation for all of the European countries, and then really the business started to develop because the processes were there for biodiesel and bioethanol, and now there was also a reason to do so. There were some subsidies and help and innovation funds to build up this industry, but it was really built up because it was a political will to have more renewables in the energy sector, and that really succeeded, and that's why we have roughly 10% renewable fuels now in Austria. The most relevant is biodiesel still from oil crops. with the co-product animal feed and chemicals, and we have also very much used cooking oil. So we really established a big collection of waste cooking oil all over Austria, and we spread this also to the neighboring countries, because you know Austria is in the center of Europe. So we also introduced these logistics in the neighboring countries, quite a good location. Hydrated vegetable oil we do not produce in Austria, not yet. Our oil refinery, they want to do it, but not yet. So we are importing this from I think in the Netherlands and in Finland. They have two big facilities. We have a little bit of biomethane mainly from maize and agricultural residues, but this is very, very little because we have no no cars running on compressed natural gas. And so we cannot bring it in the transportation sector. Normally the biomethane is injected in the natural gas grid and used for heat and power, but not in the transportation sector. And the second biggest thing we do in Austria is bioethanol. We have a very big bioethanol complex also on the river Danube, where we make at least conventional bioethanol. So they started with corn and wheat in the very beginning. And then they started to further develop a starch factory, a starch biorefinery, because out of starch you can make so many different other products. And they further used this and use only residue stream from the starch for ethanol production. And they also started to collect the CO2, which you normally don't use, but they started to collect the CO2 because there's a big market also for CO2. In the beverage market and for technical applications, so they also use the CO2 as a very valuable product. Secondly, we also make bioethanol from black liquor. Black liquor is the remaining part in the pulp and paper industry which you cannot convert to paper. But in some specific processes, they also have sugars in this black liquor. And these sugars can be also converted to bioethanol. And we have one pulp and paper mill in Austria that converts the black liquor into bioethanol. And the remaining fraction still can be used to make electricity and heat. So the conventional way was only make electricity and heat. And now they first ferment it and then use it for electricity and heat, and they have a very good greenhouse gas balance. They have 98% less greenhouse gases than conventional gasoline. So 98% reduction because it's a residue stream out of a pulp mill. And I only believe this 98% because it was calculated by my colleagues and me, so we really know the details, so we can be really sure that it's really a greenhouse gas saving of 98%. At least the amount is limited because the amount of pulp they produce there is limited, so also the amount of ethanol they can make, but it has a very high market value in the meantime because everybody is looking for bioenergy carriers with a very high greenhouse gas saving. So this is at least common technology today, and we have some research activities on converting wood and straw into bioethanol, but this is still on in Austria at least at a very low level. We do more work and we build a very good testing facility on Fischer-Tropsch diesel, where we gasify wood and make this broad portfolio from chemicals and different fuels. So, but this is still in the research phase. Yeah? So we are still researching and developing that and to further develop. So at least summarizing, biodiesel and bioethanol are the key biofuels we have nowadays in Austria. We nearly have in total, we are blending this to B7, 7 volumes percent in diesel, and E10, 10 volume percent in gasoline. That's the way we're entering the market. So the big question is always, what is the big benefit if you use biofuel in comparison to a fossil fuel? And with your background, you will be able to answer the first question: how much CO2 is emitted when you burn 1 liter of gasoline? Yeah. So did you ever think when you burn 1 liter of gasoline, how much CO2 you're going to create? Pardon? is the main content of gasoline? It's carbon. Yeah? So if you burn one carbon molecule to CO2, it gets heavier. Yeah? How much heavier is it getting? From 12 to oxygen is 16. 12 is the carbon, and the CO2 is 44. Yeah. So the weight increases by a factor 3.6. Yeah. So if you roughly say 1 liter of gasoline is 1 kilogram, a little bit less, and you triple the weight, you get chemically or physically or chemically at least 3 kilograms. Yeah. So if you burn 1 liter of gasoline, you get 3 kilograms of CO2. And that's bad. That's bad. And the second question is, if you burn 1 kilogram of dry wood, yeah, how much CO2 do you get? You have 1 kilogram dry wood, so no water in it, so it's really the wood. And this chemical formula of wood, what is a key element in the chemical formula of wood? Yeah, but it's carbon, hydrogen, and oxygen. Yeah, okay. So if you have 1 kilogram of wood, roughly, how much is oxygen in that wood? It's roughly half of it. Yeah? So if you have a piece of wood, the half of it, you carry it home, 1 kilogram, but half of this kilogram has no heating value. Yeah? So you have to carry it, but it's only oxygen. Yeah? So this kilogram of wood only has half a kilogram of carbon. And if you burn half a kilogram of carbon by tripling or 3.6 the weight, you get roughly 1.5 kilogram. Yeah? So if you burn 1 kilogram of wood, you get 1.5 kilogram of CO2. And the molecule CO2 is the same for the gasoline and the wood. It's CO2. Chemically, it's the same. So the big question is, why is one better than the other? Yeah? And the reason is, if you use biogenic carbon, you're part of a natural carbon cycle. Yeah? So all our vegetation outside, they uptake CO2 from the atmosphere, and during night or when they die, they release again the CO2 in a natural cycle. So if you don't touch a forest or a field, more or less the carbon cycle is closed. Yeah? It also releases CO2 during the night, during winter. So this is the natural biogenic cycle. And if we now use the piece of wood for energy generation, yeah, we do the same thing. We just oxidize the carbon. We add oxygen, and we make the CO2. Yeah? And the only difference is that this happens very quick. Yeah? If you burn it, it disappears. Yeah? So it's also a question, how long does it take until the carbon cycle is really closed again? In agriculture, it's easier. If you have an agricultural field here, and you make an energy carrier like biodiesel or bioethanol with the raw material, after 1 year, when in agriculture the rape and the wheat is regrowing, at least the carbon cycle is closed within 1 year. Yeah? So for agriculture, it's the same for our food. All the food we eat, finally it ends up as CO2. Yeah? And that is always part of the biogenic carbon cycle, so there is no accumulation of CO2 in the atmosphere. Yeah? This is why this biogenic carbon is, so to say, the good carbon, because it's in the cycle mainly influenced that the photosynthesis is uptaking it. Yeah? And it becomes more difficult if this is in a forest. Normally in the forest, the trees takes you 80, 90, 100 years till they grow. Yeah? So it takes 100 years that the tree is grown. If you don't touch the tree, it falls down sooner or later, and it will disappear as CO2 after 20 or 30 years or however. Yeah, and then the cycle is closed. If we burn this tree, the whole CO2 which was accumulated in the last 100 years is emitted at one time in the atmosphere. Yeah? So it took us 100 years to collect it in the tree, but when we burn it, it's in the atmosphere, and it takes, when you replant it, it takes another 100 years that you have the carbon cycle closed again, or to have the carbon stored again in the tree. And this is the tricky thing, that when you use forestry biomass, that you might have an increase of CO2 in the atmosphere for a certain time, yeah, until it's again uptaken. And so in principle, for agriculture, it's closed in 1 year. And for forestry, it might take up to 100 years if you look only on one single tree. If you look on the whole forest, yeah, with young trees, old trees, big trees, small trees, depending on the relation how much you take out and use for energy, compared to what's still remaining in the forest, uptaking CO2, if this relation is in an equilibrium, yeah, then you have no CO2 accumulation in the atmosphere. And this is the tricky thing, not use more wood than is regrown in a certain area per year. Then you can be sure that the CO2 concentration remains stable in the atmosphere. Yeah? Because all these CO2 flows you see here, they are a function of time. And we don't want to have CO2 accumulating in the atmosphere. Yeah? So at least the emissions and the uptake must be in an equilibrium. And even for a country like Austria, where we have 45% of Austria are covered with forests, and we are very few people, we are only 8.5 million people, yeah? But at least we should not take more wood out of the forest that is regrown year by year. And this is a tricky balance, because the forest has younger forests, older forests. It's a big mixture also of different species. And this is really the tricky thing. To have a really sustainable biomass system means a sustainable forestry system. And the minimum criteria is always that you replant. Yeah? So if you cut down a forest, you must replant it again. Yeah? And you know, they start being like this and it takes a long time. But the replanting is very essential. If you just cut it down and use it, that's not sustainable at all. And this really needs a good, sustainable forestry management to have the possibility to keep this biogenic carbon cycle in a balance. And this was, when I was young, there was no discussion on that, because people said if you emit and it's recollected via photosynthesis, it must be zero sooner or later. Yeah? And I would say 20 years ago or 25 years ago, people start to think about it, and they found out it's much more complicated because of the different timing of the different processes to really make sure that the forestry biomass is sustainable. And additionally, it comes that, of course, the forest also store the carbon. Yeah? And if you make a chair or a table out of the carbon is still stored here. Yeah, so this is still a storage, and as long as the carbon is stored, you don't have a problem. The problem starts when you burn the chair to use the energy, then the CO2 ends in the atmosphere, and then you have to rethink, is it good or bad to burn wood? Yeah? And we were discussing if the old furnitures we inherit from our grandparents, very nice furnitures, yeah, if you burn them, it's bad for the environment because the CO2 was collected maybe 200 years in the past. Yeah? So and now you add it again in the atmosphere, so you have to regrow many trees at the same time. The main message of all this, with the forestry, it's very tricky to guarantee that the CO2 balance is closed. And in Europe, we have developed a very specific system to count the biogenic carbon emissions. It's also part of the national inventories of greenhouse gases, because each country, India, Austria, Europe, they all have to make annually a greenhouse gas balance. So they also have to count for the biogenic CO2, mainly reporting how much carbon is stored in the forests, and to see if there's more or less carbon stored in the forest, if this is really in balance with the amount of forest you use. So, and this is at least reported in the national inventories. So in the past, we did not report in LCAs on the biogenic carbon. We just said it's zero and forgot about it. But nowadays, it's also important to count for the biogenic carbon. Yeah? Even if you say it's first uptaken as a minus and then it's released as a plus and totally the carbon is zero, it's still important to now report also on the biogenic carbon flows and to further analyze if the system really is closed. And to really allow a closed carbon cycle, I mentioned the word certification already in the morning, it really needs a system that guarantees that the biomass you use is grown sustainably. Yeah? There's really a system in place now to avoid the risk of unsustainable biomass production. Yeah? That's why with the biomass also the LCA and all the environmental issues are much more complex, because you're always interacting with the biosphere and nature compared to hydropower or wind power, which is a pure technical thing, more or less, to really make sure that the carbon cycle is closed. Yeah? On the medium term and on the long term and on the short term, because we do not need additional carbon in the atmosphere, even if it comes from biogenic sources. Yeah? So and that is at least the big challenge for that, and this now in many areas in the pulp and paper sector, but also in the wood sector and in the energy sector, more and more certification is taking place, that at least each piece of wood needs somehow a certificate showing that it's replanted and coming from a sustainable management forest. And if the system works properly, of course, then it's really guaranteed that this has finally a good sustainability balance or greenhouse gas balance or other issues. And this was at least also a key driver when in Europe we started to introduce biofuels. And as I've mentioned before, 15 years ago, Europe wanted to have more renewable energy in the transportation sector. And this was the law, it's the Renewable Energy Directive. And it's a legal document. And you know, to read a legal document is not that interesting. So if you see that, you can look, the annex is the interesting of this legislative, because it's the first legislation document which needs an LCA approach in the annex, because it gives you a regulation for putting biofuels on the European market. And for each liter of biofuel, you need a life cycle assessment stated by law, because already at this time in 2009, they knew that not each piece of biomass is sustainable per definition. No, it has to be certified, it has to be managed and calculated. And here in this Renewable Energy Directive, in the annex, you find the formula of the life cycle greenhouse gas emissions of a biofuel. Yeah? And so this was the second time I was happy in my career. Yeah, first, I was the first one being exotic at university, making life cycle assessment. But 20 years later, life cycle assessment was part of a European regulation, because everybody realized that life cycle assessment is necessary to guarantee sustainable products, to guarantee that the biofuels reduce greenhouse gases. And they have been very clever at this time, because at this time you can imagine, because the farmers are involved, the industry is involved, everybody complained. Said, ooh, boo, that's so difficult, But they say, okay, we make it a little bit simpler. Yeah? So they simplified the approach a little bit. And then they said, it's easy for you because you have only to have a saving of 35% greenhouse gases compared to gasoline or diesel. And I said, bah, only 35%, this is not that much. Yeah? You build up a new industry and you're only saving 1/3 of emissions. I was a little bit annoyed, saying only 35%. But they have been clever, because they said in the beginning, it's 35%. After 5 years, it was 50%. Then it was 60%, and now it's 65%. So as once you have introduced the system, At this time, everybody was sure we can reach this saving. Yeah? To reach a saving of 30% is easier, but to reach a saving now of 65%, you need a good technical process. You need a good feedstock. So this was a very good idea to start with a low target on the beginning and increase the target. With new feedstocks and so on, they reach the target also nowadays, and the system is running all over Europe. And each liter of biofuel has an LCA with it. And if you buy it, you get a price and the greenhouse gas emission, because you have to make sure that each liter is used properly. Okay, another aspect besides greenhouse gases, about the competition, biofuels, as you've seen, can use raw materials that can be also used for other purposes. So it's also a question of land use, of land occupation. So how much hectares do you need for 1 kilometer or for one year or so on? And so the discussion started about land use. And to make a proper calculation on land use is a very tricky thing, so to say. And in this development, you've very often found graphs like this. Yeah? And they tell you that how many kilometers can you drive when you occupy 1 hectare per year. Yeah? And they compared the biodiesel made from rapeseed, ethanol from wheat, ethanol from wood, the synthetic diesel from wood, the synthetic diesel from black liquor, from the pulp and paper industry, or the DME, dimethyl ester or methanol from wood and black liquor. Yeah? And they found out that the DME needs, you can drive the longest distance with a big truck per 1 hectare. And you see the biodiesel looks very poor. The bioethanol looks very poor. Yeah? And the big question is, could that be? Is it so simple? And then you say, okay, let's see. The wood grows in the forest. So the hectare must be 1 hectare forest. The wheat and the rape, they grew in agriculture. So the hectare is agricultural land. But there's a difference if you have a hectare of forestry or a hectare of agriculture. So a hectare is not a hectare. Yeah? So the first thing is, this is not fair because it's not the same hectare. Yeah? If you have a forest there or an agriculture there. But secondly, if you find here black liquor, I've never seen a black liquor tree in the forest, because black liquor is not growing in forest. It's a side product of the pulp and paper industry. So how can they allocate a hectare to a residue from the pulp and paper industry, which makes pulp and paper? So the question is, how much is from this hectare is going to the pulp? How much is going to the black liquor and so on? So this is at least not a fair comparison. And we know when you make biodiesel or ethanol, we always produce animal feed. So how did they count for the animal feed? Because on this hectare, due to the technical characteristics, yeah, when you make 1 ton of biodiesel, you make 2 tons of animal feed. Yeah, so on this 1 hectare, you have the double amount of animal feed, so you have to allocate somehow the hectare also to the animal feed. The same with the ethanol. When you make 1 ton of ethanol, you make 1 ton of animal feed. So it's a 1-to-1, more or less. Yeah? This is also not seen for that. Yeah? So the main message is, we will talk about land use change during the week. This comparison, really be fair, really be careful and see if it's really a fair comparison. And you can imagine who made this one. Yeah? It's a company. They make the DME and the methanol, yeah, and trying to say we are best, most efficient in land use. But as young scientists, yeah, here at university, you really have to ask question: what is the hectare? How did you consider the byproducts? That's the important thing. to ask questions, think about, and then say this is not a fair comparison. To be honest, to make a really fair comparison on that is a very complicated issue, because you have so many products. From this, you start with a hectare, you make rapeseed, but then you make glycerin, biodiesel, and animal feed from the same hectare. And how can you say, okay, this part of the hectare, I give this to biodiesel, this I give to animal feed? You need to think how you do it in a robust scientific way, say how much of my hectare can be allocated to these three products. And this is not trivial. This needs, and we will talk about allocation, and for land use, of course, it's very essential, and a thing like this is a little bit too simple, so to say, too simple. Okay, what is the current demand on biofuels? The current demand on biofuels globally, the big bioethanol production started in Brazil and in North America, because they wanted to get independent from raw oil imports. That was the key drivers in the 80s. It was not environmental protection, it was energy security. Mainly in America and South and North America, to secure energy security, use own feedstock and make ethanol. That was developed in Brazil using sugarcane, and in North America using mainly corn. And Europe was a little bit late on that, but this is more or less the development of biofuels from 2016 up to today. So we are in the middle. This is today. And it's expected in future that it will slowly develop, as already a significant potential is already used from the different countries. And you see that the light blue is bioethanol. This graph is in liters per year. The ethanol has the highest share, and the dark blue is the biodiesel, and the light green is the renewable diesel, is this hydrated vegetable oil. You see, this is the smallest part so far. And in future, we expect also more advanced biofuels. But it's in liter. And you know that if you do the same graph in energy units, in terajoule units, you will see that the ethanol is having 25% less energy than the biodiesel. Of course, then the relation would be in favor of biodiesel, but still the total amounts of biodiesel on the global market is less, or significantly less, compared to ethanol. And if we have such big amounts of biofuels on the market, it's also a question which are the leading countries in that area. And here in that graph, there's 3 time periods distinguished, and the orange-yellow part are the advanced economies, how they call it, which is mainly the United States. Europe was a front runner in the past, but in future it's expected that the other economies, the emerging economies, are speeding up and also developing. You see, India here is the light green one, and this is a graph from the International Energy Agency. So this is the expectation that India will produce significantly amounts of biofuels in the future. So it's very important for you to be familiar with this area, that you can make good life cycle assessments, and to guarantee that the future produced biofuels in your country really fulfill the necessary sustainability indicators. And the question is, if you make now a greenhouse gas balance of these biofuels, you will find here, this is the graph for bioethanol, and in comparison to petrol, in the average situation of all 27 European countries. In EU, it's different in each country, but this is the average so far. And you see here 2 things. One thing are the greenhouse gas emissions, given in grams CO2 equivalent per kilometer. So how much greenhouse gas emissions per kilometer do you have when you drive 1 kilometer? On the right-hand side, you see the primary energy demand, accumulated energy demand, which is a matrix for the energy efficiency. That means how much energy I have to take from nature to drive 1 kilometer. Yeah? So, and this is very important because the message from greenhouse gas emissions and primary energy is a little bit different. Yeah? Is the first message. And the second message is here, the lowest column here. This is pure gasoline, and up from is pure ethanol. Yeah? And in between we have the E5 and the E10 as a blending, as the average feedstock mix we have in Europe. And you see that the ethanol production, or the ethanol is roughly having 20% less greenhouse gas emission, not 250, roughly 200 grams. Yeah? So still, there is much greenhouse gas emitted when you make bioethanol. The main reason is that the ethanol production needs much energy for the distillation, and commercially in Europe, it's still mainly natural gas being used for that because it's the most economic way, not for environment, but for the economy. So therefore, they do not use the whole possibilities of ethanol. But secondly, this is a life cycle assessment per driven kilometer. Yeah? So also the vehicle itself, to make the vehicle and to dismantle the vehicle, is included in that calculation. Yeah? Because you have to build it, and we build a normal gasoline car until it ends in the car shop. It has already 10 tons of greenhouse gases emitted to build it. Yeah? And this is also considered here per kilometer via the lifetime mileage. In the LCA, you will learn all the details. So this is a first taste of life cycle assessment and a result on greenhouse gas emissions. On the other side, you see the primary energy demand. Yeah? In the case of ethanol, the primary energy is the corn you get. Yeah? This is the starting point, the heating value of the corn. So how much heating value in the corn you need to drive 1 kilometer. Whereas for the petrol, the very first one, it's the raw oil. So how many megajoule of raw oil do you need to drive 1 kilometer? And you see the process of making ethanol needs the double amount of energy compared to raw oil, which is for some people in the very beginning a little bit astonishing. Yeah. Secondly, it needs some effort to make something liquid out of corn. Yeah. That's why you need to put energy mainly in the cultivation phase of the corn, but also in the distillation, in the bioethanol production. Whereas when you pump up raw oil, everything is liquid and ready already. So nature has done most of the work for the fossil. Yeah? But still, it's significantly higher. But the main difference is that in the case of bioethanol, it's renewable energy. Yeah? And renewable energy, we know, is better than the fossil energy. So therefore, the maize is having more energy, but 90% is really renewable energy. And we will learn later on when we talk about an indicator of primary energy demand, you will learn about how necessary it is to distinguish between the fossil and the renewable part. I show you the same picture now for diesel and biodiesel. And normally the diesel cars are a little bit more efficient, so the values are a little bit lower, so it's a little bit above 200 grams per kilometer. And then we have the biodiesel, the B7, and then we have the pure HVO, the pure farmer using the European raw material mix. So the reduction is roughly 25 to 50 grams, so the reduction is a little bit bigger than for the bioethanol. And the upper front one is for Fischer-Tropsch diesel, which is not commercially available, but if you use wood and convert it to Fischer-Tropsch, you have an emission significantly below 100 gram. And with the primary energy, it's the same. All the biofuels have a higher primary energy demand due to the conversion efforts compared to the fossil diesel, but still this type of energy is nearly 100% renewable. Also, very important message of this graph is, you see, I make a range for the results. So I don't give one single number. We made a range. Because we will learn when we talk about life cycle assessment, at least to end up with one value, if you calculate it, you get one value. But if you lean back a little bit and you see, okay, I'm interested in significant differences between two systems, and then you have to think, what is a reasonable range? If I change my assumptions a little bit to see if there's a significant difference, if one is here and one is here, you say, I'm sure this one has lower emissions than this. If it's something like this, you have to be honest saying, I'm not sure if there's a difference. Yeah? This is very important also in LCA to see what are significant differences. And the difference starts to be significant 10% and more. If it's only a 2 or 3%, that's not. It must really be significant. And if we have to reduce greenhouse gases by 80%, we're looking for systems that have significant reductions. So also in our consideration, we need to have significant differences. You can make the same calculation on greenhouse gas savings. I found this graph made from the International Energy Agency. They have many activities in the area of biofuels, and these are different countries. There is also India in there and other countries. And really depending on the feedstock and the baseline, you see how much the different energy, biodiesel and ethanol in average can save greenhouse gases. And here you see values between 40% up to nearly 80%, yeah, because depending on the feedstock. And here you also see this is South Africa. In South Africa, the baseline for South Africa, the diesel and gasoline for South Africa is so much higher because they make gasoline and diesel out of coal. And doing so, you have significantly, I would say 60-70% more emission if you make from coal gasoline or diesel, or if you make it from raw oil. So this is at least the reason why there the biofuels even have a bigger saving. The production is process, as I mentioned before. This is the Fischer-Tropsch process they apply here in South Africa. So I'm on the end of of this lecture by summarizing a little bit the take-home message for today. It's important to know there are many different types of biofuel, of transportation biofuels. Yeah? So you always have to be clear what is the transportation fuel you're analyzing. There are so many different raw materials, yeah? So you also have to know the different raw materials they are made from. They have different properties, they have different conversion processes, they have different criteria for sustainability, and in between there are many different conversion processes. Yeah? And when you talk about a biofuel, it's always important to really specify the raw material, the biofuel, and in most of the cases also necessary to specify the conversion process. And that will be what we will learn tomorrow when we talk about biorefinery, how to do that in a harmonized, in a common form, because it's so important that you always talk about the same thing when you talk and discuss with others. So you really have to be precise in specifying. Then we have seen there are 3 key value chains for biofuels. It's the oil and fat-based chain. Yeah, they use oil and fat chain. Then is the biochemical conversion, where the core process is the fermentation, for which you need the sugars. And the sugars can come directly from agriculture or from starch, or even in future or even today from cellulose and hemicellulose. And the third value chain is the thermochemical conversion, with the key process of gasification, where you make the synthesis gas exist being a combination of CO and hydrogen, and with these combinations you can make a broad variety of different products. We've also seen that a closed biogenic cycle is the key to have a sustainable biofuel, biomass, bioenergy system. You really have to see if the CO2 uptake from the atmosphere is nearly at the same time when you put back the CO2, the biogenic CO2 emissions when you drive your car, or if you burn the biomass, that this is really a closed cycle, and this is the key, and this is really still a challenge for the sustainability. Then we have seen that biodiesel and bioethanol are currently the most relevant commercial biofuels of today. They are made from oil, starch, and sugar crops. The hydrated vegetable oil is upcoming. It's a different process and globally not yet so relevant. I've also mentioned that biofuels in future made from lignocellulosic feedstock, because wood, and I would assume in this area the straw, is a very big available resource that can be used as a feedstock for biofuels, bioethanol, or even Fischer-Tropsch diesel. And finally, we have seen that a substantial greenhouse gas reduction is essential, and not of the systems per se give you a substantial reduction, so you really have to identify the framework conditions. This is still a challenge to maximize the greenhouse gas reduction, and of course an adequate land use. How to use the land, how to manage also the byproducts. These are key challenges for the further development and maintaining the biofuels. So this is the final slide of this lecture, and if you have any questions, now you can ask them in the big forum or afterwards also on a bilateral personal scale, however you like it.
Hello. Thank you very much for a wonderful talk related to biofuel production. So I have one doubt that one of the primary steps for production of biofuel from biomass is the pre-treatment. Right. Let's say if we consider from lignocellulose, if you want to produce bioethanol, we need to do the pre-treatment at the initial stage. So that pre-treatment step, can you comment on the sustainable methods for that pre-treatment? Conventionally, we have a chemical, thermochemical, or combination of them, or biochemical. But what are the current trending sustainable methods for the pre-treatment of lignocellulose material?
The sound was very bad, so I'm not sure if I understood your question quite well, because it's...
Okay. Sorry, what are the trending sustainable methods for lignocellulose pre-treatment? Pre-treatment? Yes.
I'm not sure if I can answer this question completely. I made several LCAs on pre-treatment methods. I cannot say per se which is the best one, because it really depends on the overall process. What are the different products you can make out of it? What are the amount of product streams? And also what is happening to the non-usable stream? Yeah? So it's in an LCA, it's just one out of the whole process. And normally, if you have different pre-treatment methodologies, you have different products. Yeah? And it might be that with one system you have 3 products, and with the other you have 4. And then you need a fair comparison of a system with 3 products and a system with 4 products. Yeah? And we will learn on that in detail, and maybe we can use this example in one of the interactive work in small groups we want to do, to see the different products and how to make a fair comparison. And finally, sustainable is a broad word. So if you look on greenhouse gases, maybe one is better. If you look on energy efficiency, the other one is better. So even we have to define what are the key environmental indicators we want to analyze, and then see which of the pretreatment is maybe better than another one. Yeah.
Okay, thank you. So because why I asked recently, there are a lot of papers related to ionic liquids or deep eutectic solvents. They claim that using these greener solvents, we can easily separate lignin and from the cellulose, then ferment the cellulose to produce the biofuel. So that is right now, I don't know. I still have a doubt about that. That's why I just wanted a clarity. Thank you.
But at least the lignin is a tricky thing because you can also make product out of lignin, yeah? Or you can use the lignin to make the energy for the processing. So you can't do both because you have the lignin only once, and this is also a tricky thing. Yeah? So even the lignin is part of the overall LCA, yeah? And then it even becomes more complicated. And in most of the papers, I know that the guys who are developing a certain process, and in most of the cases in LCA say this is maybe a good one, it's the most cheapest one in all the comparisons and maybe the most environmental one. But still on a scientific way, it's a very tricky thing to compare this, but we can exercise this and see what are the key aspects we have to consider in such LCA comparisons. Thank you.
So thank you, sir. Thank you for such an enlightening talk. And I think those who are not earlier exposed to the field of bioethanol or biofuel, they are, becoming, familiar with the field, and it will, it will be better for them to, to read a few things in your hostel today, and just to clear some terms which our expert have discussed, so that you understand the concept and the future lectures in a better way. So anyway, so we had two nice talks by Professor Youngweir today, and we will continue with his talks tomorrow, and maybe we can have 5-minute break and then we will start the next lecture. Okay. Be well versed with the term that is bioethanol. So bioethanol is the ethanol which we prepare through biological routes, and if you technically see, then just a second. Hello. So technically, the most of the ethanol which whatever we are using, whether it is for potable purpose or it is for transportation purpose, it is prepared from Saccharomyces. So all most of the ethanol we are using, it is bioethanol only. the ethanol prepared through chemical routes, it is normal, you can call it ethanol. So we are concentrating, or we are pressing hard as of now for adoption of this bioethanol. Lot of biomass which is available, and the government is putting lot of effort, putting lot of funds into the research of this particular area, that is lignocellulosic bioethanol. And they are still trying to find out the question, find out the answer, that whether can we produce enough quantity of lignocellulosic bioethanol using these biomass. In European and I think in US, the people started working on this particular aspect, and they established many biorefineries based on this lignocellulosic biomass. But none of them could be successful because of one or the other reason, mainly because of the unavailability of sufficient feedstock. But we are lucky in that way that we have a very good agriculture production system with enough cultivable land and enough surplus feedstock. I'm saying not the typical LCA analysis which our expert will be discussing, highlighting the the inputs and all those things. That analysis is yet to be done with respect to the availability of feedstock and what is the life cycle of of the all these technologies in Indian scenario. But yes, theoretically we have around 660 million tons of the lignocellulosic biomass which is available, and almost half of this is you can say available for its conversion into the bioethanol. So we will discuss in bits about the technology as such, and what are the key areas as a student where you can focus. Definitely the workshop is more concentrated on the LC analysis, but some of the key things which are relevant for the bioethanol aspect as such, I'll be putting some highlights on that. So the biomass, whatever we are using, whatever we are having, we can use it for multiple purposes. Like some part of it is conventionally used as animal feed, and some part is used as industrial raw material also, and some is flowed back into the soil for maintenance of soil quality, and little part as of now is diverted towards the biofuel. Uh, it can be through traditional methods like burning. Nowadays pellets are being prepared from the biomass, and these pellets they are being used as source of energy for running the boilers in the powerhouse generation in some of the industries, and then definitely the modern liquid biofuels like bioethanol. So we can use it multiple ways, but again keeping in view our commitment towards global climate change, we have to see to it whether which of the technology is more environmental friendly, and for that we have to have the LC analysis of each and every technology which we are using. But based on the experience of based on the data of LC analysis, as our expert faculty has shown, that the lignocellulosic biomass, the bioethanol and biogas and all the biofuels, they are comparatively more environmental friendly. So we can try to establish the industry for production, for large scale production of these fuels in the India. So in that way the government is putting a lot of effort in this. And this is the result of that effort. If you can see, the ethanol blending program which was started after 2010, initially it started with 1%, then 2%, and now we are standing at 20%. Soon we will be achieving, it is at present I think 17 or 18%. But last week I think Ministry of Petroleum, they have released data, and they are sure that we will reach 20% ethanol blending by the end of 2025. So, and why this ethanol blending is important? So you can assume from this data from the ministry that by adopting to the ethanol blending, we are saving around 1 lakh crore of rupees of foreign exchange, and we are reducing CO2 emissions to the tune of 544 lakh metric tons, which is a huge number, keeping in view the global climate change. And we are substituting around 181 lakh metric ton of crude oil, which we have a very limited quantity available in our India, and mostly we are importing it from other country, and that's why it is the saving of more than 1 lakh crores. So this is the main reason why government is after the bioethanol, so that it can reduce its dependence on the import of the fuels. Then if you look at the data, the bioethanol production over the years, in this year also we are standing somewhere around 6,350 crore liters of the bioethanol, which we are producing as of now, and it is bioethanol. It is not lignocellulosic ethanol. Okay, bioethanol means which we are getting from all kind of sources produced through biological routes, and lignocellulosic bioethanol or 2G ethanol we call, it is from the lignocellulosic biomass. So it is mostly 98% is from the bioethanol, and 2% hardly we are using LCB ethanol, because only few of the biorefineries we have started till now. We'll discuss that, what are the different at what places we are having these refineries in India. And yeah, it will be clear from this. So we have different sources of this bioethanol in India as of now, and by 2017 and 18 it was C grade heavy molasses, and later on government permitted to use B grade heavy molasses, and also some of the grains it was diverted for the production of bioethanol in India. So C grade molasses is I think many of you must be aware that we get sugar from the sugar cane, right? And once we are going for pressing of the bagasse, and then again repressing. So initially first two if you remove, it is pure sugar. Initially we take out juice, and then again we are pressing, it is B grade, and then C grade, the leftover material whatever is there, it is your C grade. After getting the crystallized sugar, whatever is left, it is C grade. It is not used for the production of the sugar. So that molasses contains almost 50% of the sugar, and they are used for the production of bioethanol. So earlier it was only C grade molasses, but now B grade molasses also government is allowing to use. And recently the government is also permitting damaged food grains for utilization as feedstock for the production of bioethanol. So this is a significant shift in policies, and that was basically because earlier there was a lot of fear about the food versus fuel. Okay, it happens in US during 1970s that they diverted lot of corn for the bioethanol production, and suddenly the corn prices, they were multiple times, and the farmers, they had a very hard time to get feed for their poultry, and which is one of the staple food, meat, you can understand, in US. So just to avoid that, the government was little apprehensive in allowing the use of grains for production of bioethanol, but now they are understanding that okay, anyway it is not it is not being used for food purpose, that damaged grains in the Food Corporation of India's storage houses. So they are diverting it for this particular purpose. So the government is maybe slowly, it is very dynamic actually. When sugar prices, they are shooting up, they are stopping utilization of B grade molasses. If they are coming down, then they are again they are allowing. But it is highly regulated from the government. There is no surety that the B grade molasses will be available for the production of ethanol or not. So the industry is also very apprehensive about this, that whether we should upgrade or we should expand our bioethanol production capacity or not, because unless and otherwise you have shortage of certain raw material, then there is no use of expansion. And but as I told, we are producing around 6,300 crore liters, but our to meet the demand of 20% blending, ethanol blending, we will be requiring much more than that. More than 1,000 crore liters of bioethanol will be needed, and there are only few ways that we can achieve that: either to increase the sugarcane production, divert more of the B grade molasses for bioethanol, or we go for second generation bioethanol, or we import. So there are few choices which we have, and if you look at the installed capacity also, you will find that we have around a total capacity of around 700 say million liters, billion liters, but to meet that more than 1,000 billion liters demand of bioethanol for blending, total demand is around 1,500, but the for bioethanol for blending it is around 1,000 billion liters in crore liters. So to augment that, to reduce that demand supply gap, we have to install the new refineries so that we get the desirable amount of this bioethanol. So these are different pathways through which we can go for the installation of new say biorefineries based on first generation, which is out of question in a big country like India. We cannot divert our food sources for production of bioethanol. So one can survive without a car, but we cannot survive without a food, definitely. Then second generation is industrial waste, wood, grass, forest residues, and third generation is mainly algal based biofuels, biodiesel and biooils. And fourth generation we have genetically modified algae, which is not permitted as of now to have the genetically modified organisms utilized for large scale cultivation. Definitely in bioreactors and all those it is permissible, but when you grow the genetically modified organisms in open that on large scale, there are always chances of contamination, and all those ethical concerns are there. So that is not permitted. So we are left with only two options, that is second generation bioethanol and third generation bioethanol. Algal biofuel, definitely they are promising source, being the photoautotropic microorganisms require less of the substrate to grow, but require a lot of area to grow. So there we have a limitation of area, and in case of lignocellulosic biomass we have certain challenges. So we will discuss that. So this, I think we have a lot of paddy straw. Wheat residues as such, I would say it is not available for bioethanol conversion. Mostly it is being used as animal feed. Earlier people were burning the wheat straw also, but now the land availability is also reducing and we have good mechanization in place. So wheat straw is not available for as such for the bioethanol production. Yes, sugarcane bagasse, definitely we have large area under sugarcane bagasse, and lot of sugarcane bagasse is available, and we can utilize, you can divert them for the bioethanol production. Moreover, the advantages, certain advantages are also there with the bioethanol. Like you will get sugarcane bagasse at a particular place. When you are putting up the sugar mills, at same place we can have biorefineries, the sugarcane bagasse coming out from the sugarcane mills, that can be diverted for the bioethanol also. So you need not to worry about transportation cost. So it is highly concentrated and you can predict that how much biomass or bagasse will be available, because sugarcane cultivation in India is regulated. It is not like wheat and rice that anybody can grow and anybody can sell. It's not like, it is not the case. For sugarcane cultivation, you have to give prior information to the government that I am putting up sugarcane cultivation in this much area and I will be supplying this much sugarcane to a particular sugar mill. So it is highly regulated. You can plan your capacity, you can plan your expansion, and you can predict that how much biomass will be available for me during the season to convert the sugarcane bagasse to bioethanol. So in that way, opportunity, keeping in view the less transportation cost and the ensured supply. But on the other hand, the other feedstocks, whether it is rice straw or mustard straw, it is highly scattered, and definitely keeping in view the global climate change, reducing water availability, it may be a challenge to continue with the paddy cultivation in India. Government is giving lot of subsidy. Those who are reading newspapers, they must have read, government will provide 10,000 rupees subsidy to farmers who are growing crops other than rice. So government is discouraging the rice cultivation. So the biorefineries based on rice cultivation or paddy straw may face difficulties in getting ensured supply of the biomass. Definitely the others, they are in very minor quantities, like cotton. There is huge reduction of area in last 2 years. In Haryana only we lost 20% area last year, and even Punjab it's worse. It is 40% area reduction in the cotton due to the secondary pest resurgence and other factors. And rest of the biomass which are there in this particular graph, they are available in minor quantity and in very scattered location, and the available whatever is available, they have other multiple use among the farming communities. So we are left with two potential, say, biomass, that is paddy straw and sugarcane bagasse. And this is the process of conversion of, say, I would say, how the cellulose and lignocellulose and lignin, they are packed inside the plant cell, and cellulose is around 30 to 60%, 15 to 35% is hemicellulose, and lignin is 10 to 30%. And as our guest speaker also told, lignin is a very energy rich compound. We can use it for multiple purposes, but in a biorefinery setup, it is the main hurdle which is to be removed from the plant material, converted into the fermentable sugars. Similarly, hemicellulose, though it can be used by utilizing co-fermenting yeasts, but the main focus as of now is on cellulose always, which can be easily which can be converted to C6 sugars and can be fermented with traditional Saccharomyces cerevisiae, which is a mature technology, I would say. So if you look at the all these steps, we can utilize these the lignocellulosic biomass, but at this we have certain challenges at each step. So the first step, as Dr. Arun was also asking, the pre-treatment is one of the most challenging step, and multiple technologies, they have been documented. and removal of lignin like biological pretreatments. But the main problem with that technology is longer residence time. You require 7 to 10 days to achieve delignification of the biomass, and no industry can survive if you are putting up substrate for a one step for 10 days. So it's very difficult. So it is always like you have to process biomass in million tons. So you require minimum residence time for a particular process, whether it is pre-treatment or saccharification or the fermentation. So we at present, as of now, I think most of the pilot scale and commercial scale biorefineries, they are sticking with the dilute pre-treatment methods. Then the second step, which is saccharification of the biomass. Once you have the lignin removed from the plant part, it has to be converted into the fermentable sugars, and for that also you can use the concentrated acids. Again, not a very environmental friendly method, very corrosive, and you require special equipments to carry out that process. So the better environmental friendly alternative is enzymatic saccharification using celluloses. That requires around 2 to 3 days for conversion of 70 to 80% of cellulose and hemicellulose to the fermentable sugars, and we have quite a number of options of celluloses now, but the mainly the commercial cellulose which is available is from Novozyme, and that's there are multiple cellulose cocktails, Celic, CTEC. So they are the pioneer in providing the enzyme solutions for lignocellulosic biorefinery. And then definitely the fermentation is mature technology. You utilize saccharification cerevisiae to achieve the fermentation. But here also, as I told, the inhibitors produced during the pre-treatment, they are very detrimental for the fermentation, and you have to look for the yeast strains which can tolerate more of these inhibitors without affecting the bioethanol production efficiency. So the few of the limitations I have mentioned here, like high utility requirement, so it is a cost intensive process. Then feedback inhibition from these inhibitors is again a challenge and a time consuming process definitely, but if we have to protect the environment, we have to reduce dependency on the fossil fuels, we have to go for it. Then this is the group of lignocellulosic degrading fungi. So many of you must have read during your courses also. So we have three major groups which is involved in lignocellulosic degradation: brown rot, white rot and soft rot fungi. And generally this brown rot fungi is enzymes from brown rot fungi. It is utilized for saccharification of the biomass. Though bacteria, they are also reported to produce these cellulase enzymes, but they are normally cell-bound enzymes and not that much effective in the degradation. Under natural setup, yeah, definitely they carry out a substantial part of conversion of this lignocellulosic biomass to fermentable sugars, but not many commercial formulations from the bacterial sources it is available in the market. So these are the three enzymes. So cellulase we normally call this complex. It is not a single enzyme. It is a 3 enzyme mixture consisting of endoglucanase, exoglucanase and the beta glucosidase. So each enzyme carry out a separate So endoglucanase, it cut the cellulose chains randomly. Then exoglucanase, it act from the non-reducing ends, producing cellobiose. And finally, the beta glucosidase, it convert the cellobiose to the glucose. So this enzyme complex, though it is theoretically it is able to convert all the cellulose and hemicellulose cellulose into the sugars, but always we have hemicellulose is associated with the cellulose, So we have to utilize certain accessory enzymes also, like xylenases, then arabinofuranosidase, manases, to improve the saccharification efficiency. So it is always a cocktail of enzymes which synergistically act to produce the C6 and C5 sugars. Then one of the interesting area where we are largely dependent on the foreign players, that is cellulose production, and it is the most important enzyme in the lignocellulosic bioethanol production process. And if you look at the projections, we will be uh, using the cellulose enzymes to the tune of 32 billion USD. So it's a big number, and we are most of the times we are dependent on the foreign players like GIAN CUH and Novozymes. So one of the important area where we can have some good enzyme producers, and we can uh, use it for large scale production of these enzymes. So these are some of the enzymes which are commercially available from Novozyme, Merck, some Yakult, and Creative Enzymes, and GIAN CUH. But most of the market is captured by first three: Salic, CTEC2, Cellulocast, and KR enzymes. Some of the key players in India also, we have advanced bioenzymes, Biocon, ultra freeze enzymes, KPs, Noor enzymes, IFF, and MAPS enzyme. Prior to 2015, there were only two Indian players were there, but now many people, they are coming up and setting up this cellulose production industries. So this is just for comparison of the available enzymes in the market, and you will find the CTEC is always having a very high activity in terms of FPU per ml compared to the other alternatives which we have in market. Now this is the present status of 2G ethanol production in India. We have 3 refineries as of now which is set up by Government of India. Panipat 2G refinery of capacity 100 kiloliter per day. It is in function, it is working, though not at 100% capacity, but it is running at around 60 to 70% capacity as of now. Then Bhatinda refinery, it is yet to be commissioned fully. Then Bargarh Odisha refinery, again it is it is under construction. So capacity using these biorefineries. So still there is a wide gap between the demand and supply of 2G ethanol, and the future of 2G ethanol in India, I would say, will depend on success of these 3 refineries at Panipat, Bhatinda, and Odisha, because assured feedstock supply is a very big issue. You need a big catchment area to run the industry 365 days in a year. So that much feedstock availability is has to be ensured by the government, because rice cultivation is again scattered. So if you look at the catchment area of Panipat, farmers, the government is procuring the paddy straw from the farmers at 1500 rupees per acre as of now. They have they are giving this rate only, which is not say very remunerative, and that collection and then transporting to the nearest center will again cost a lot of money. So why the farmers would bother to take that much of biomass and transport it to the nearby center, though they are supplying the balers to the local farmers in each village. They are supplying 1 or 2. Government is providing subsidy for that, but I think it will take time to adopt the technology, adoption of technology by the farmers is a little bit tricky always. They may or take it, or they may not take it. During November, December, you might be seeing the pollution thing, and now the government is little bit harsh and very hard on that aspect. So they are not burning it, but burning of this biomass is not by choice for farmers, it is by compulsion. They need their fields clear before the sowing of wheat, so they are doing for that purpose only, and the only solution for that is the mechanization. So unless and otherwise we go for mechanization for harvesting, mechanization for baling and transportation, proper transportation and storage of paddy straw, it will be a challenge for the refinery to run uh, throughout the year. So let's see what will be the fate of these two 2G bioethanol ethanol refineries. Maybe in 2-3 years the picture will be clear. So this is some of our work. Maybe we can skip that. So what are the opportunities, and how can we really work in that particular area? Is that we have to look for the enzymes which can be utilized for large scale production of the enzymes at site. Wherever we have refineries, we can set up the enzyme production units also. And again, process optimization for scale up, again a big challenge. Like you cannot use the same machinery for sugarcane bagasse and for paddy straw. Paddy straw contains 10 to 12% silicon. So silicon is very corrosive, and its disposal is very challenging. When we do lab experiments, it's very easy to do 5-10 grams we are taking, and you hardly see any silicon, right? But when you take up 100 tons of the paddy straw during the pre-treatment and then saccharification, you will have hundreds of kg of silicon, which will choke your filters, which will choke your machinery. So to remove that silicon, again a challenge. And that too, even for the rice we have different varieties. Some of the high yielding varieties, they have more lignin. Basmati rice has got less lignin. So we have to have tailor made solutions for pre-treatment, for saccharification. So that aspect is also untouched. We are generally we are saying, okay, this treatment is good for this crop, this treatment is good for this crop. So it may not work for a big country in India, like India, where we have very diverse variation between the varieties, composition of biomass between the varieties. And using the same machinery for sugarcane bagasse and paddy straw, again it's out of question. Or both of these, they have very different composition and require different set of treatment. So again, the ensured supply of the biomass for sustaining the operations of big biorefineries will be a challenge. Then formulation development for these cellulases is also a challenging task you can take up, and definitely commercialization will be possible only if we have ensured feedstock and cheaper enzymes and tailor-made solutions for the different biomass whatever we are having. So thank you. This was in brief about the present status, and we can have some questions now. Ashok, sorry, Dr. Ashok. So at present we are using dilute acid treatment for the pre-treatment purpose. Yes, yes. So because very uh, biological treatment, it's a very good way, but again residence time is a problem. Ionic liquids, you are telling, yes, it's a very good option, but again the cost of those ionic liquids is is very high, and it is not viable to utilize those costly chemicals for pre-treatment. It will increase the cost. Yeah, cost is very high. Yes, definitely. Any more questions? So anything left? We have 10 minutes more to go for tea. You can ask any more question from our guest also.
So as we discussed the ethanol blending with petrol and sometimes with gasoline, the ethanol blending with petrol isn't contribute to greenhouse emission, and why don't we just use 100% ethanol?
And Preeti, and see, um, it's possible. In Brazil, I think we are using petrol with vehicles with which are running on 100% ethanol, and some part we are using vehicles which are running on 85% ethanol. So that will require a complete shift to those vehicles, which will require specially designed engines and all those. So that complete shift is not possible as of now. And the secondly, we are struggling to get 20% ethanol blending. So we have to have ethanol also, no, for that. So in a shift wise manner, we have to shift our crop rotations. We have to really have some viable and sustainable technologies for conversion of the biomass into bioethanol. Then only we can think about moving towards 20 and 25. Government is very keen. Those who are following Nitin Gadkari and Ministry of Petroleum, they will realize he is after bioethanol just like anything, and now hydrogen also. So he want everything to run on the bioethanol and biohydrogen. But we have to ensure the supply. There is no point of importing bioethanol from China and then using it for the transport purpose, right? So it has to be a viable solution. So slowly we can shift the cropping patterns. We can slowly build up the capacities to produce that much of ethanol, and then only we can move in a better way. Yeah.
The environmental benefits are the same if you use it in pure form or if you blend it. Yeah, it just depends if you have 1 liter of ethanol. If you use it purely, due to the technical difficulties, but or if you blend it, it's just depending on the amount of ethanol you have, because per liter of ethanol you save a certain amount of greenhouse gases compared to gasoline, and it does not matter if you blend the gasoline or if you use it pure. That's important.
Yeah, there are obvious greenhouse gas emission benefits from using bioethanol, as professor is telling. But again, it has to be viable, and it has to be theoretically and practically possible for us to shift to that. Yeah, okay, we can.
Just last question. So, if when we see in the literature here and there, the process of conversion is multi-steps, right?
Yeah.
So some authors are proposing single step without lignin. Don't need to separate the lignin, but still we can convert. So I don't know what is the single step process to to decrease the energy consumption. They are suggesting a single step strategy.
Yeah, actually there are multiple ways.
Can you please?
You can use separate saccharification and hydrolysis. You can use a single pot method also. But you see, without removing lignin, you cannot achieve even 40% conversion efficiency, saccharification efficiency I am talking, leave about fermentation efficiency. Even 40% saccharification efficiency is a very big task in presence of the lignin, because the lignin binds to the cellulases. It reduces the efficiency of the cellulases. Moreover, the accessibility of the cellulase enzyme for the cellulose is also less in presence of the lignin. So unless and otherwise you remove the lignin, you loosen up the structure of lignocellulose, it's not possible to achieve saccharification, high saccharification efficiency and high fermentation efficiency. So those are theoretical things. They looks good in bioresource technology papers, but practically it is very difficult. Okay, yeah. Yeah, okay, thank you. So let's wait for tea, and maybe we have a few minutes left. The participants, they can introduce themselves so that they can get to know about each other. Name, the class, the affiliation, and basically you are from.
From MSc second year, microbiology.
Good afternoon, everyone. This is Pragya Sharma, studying in microbiology semester 2. I am from Bihar. Thank you.
Hello everyone, I am Diksha from MSc first year and I am also from Haryana.
Hello everyone, myself Preetima Sammal. I am from Odisha. I am currently studying MSc microbiology in first year and I am from Central University, Haryana.
Good afternoon, everyone. Myself Harshita Nagar. I am from this university only and I am from UP.
Very good afternoon to everyone. I am Dr. Ashok Babati. I am from Hyderabad. I did PhD in chemistry, but I worked a lot of things related to biophysics. Currently, I am an assistant professor in Department of Chemistry, Central University of Karnataka. Thank you.
Good afternoon, everyone. I am Ankita Thakur. I am from Bihar and I am pursuing my master's in microbiology from this university only. Thank you.
Hello everyone, I'm Garima and right now I'm doing my master's in microbiology from this university only, and I'm from Haryana. Thank you.
Hello everyone, I am Anusha. I'm a research scholar from Central University of Haryana. I am basically from Kerala.
Warm wishes to all. My name is Yatin. I'm in fourth year PhD microbiology. I'm working in the field of molecular microbiology.
Hello everyone, myself Sachin Mishra. I am a student of MSc Microbiology. I am from Ayodhya, Uttar Pradesh.
Hello everyone, I'm Priyanka. I'm doing PhD from Central University of Haryana in microbiology.
Good afternoon, everyone. My name is Ayush Mathur, and I'm doing PhD from Central University of Haryana. And my research focus is like biofuels and valorization of biomass. Thank you.
Good afternoon, everyone. My name is Amanjot Kaur. I'm working on basically biofuel production from lignocellulosic biomass. I'm a PhD student from Central University of Haryana itself.
Good afternoon, everyone. I am Kavita. I am pursuing PhD from Kurukshetra University and I am from Haryana.
Hello, everyone. I'm Monica Chahar. I'm basically from Haryana and I'm a second year PhD student at Kurukshetra University.
Hello, everyone. My name is Manisha and I am from Central University of Punjab.
Hello everyone, this is Zahiruddin Sheikh. I am a PhD
in Mental Sciences at Central University of Haryana and I belong to Rohtak.
Hello everyone, my name is Meena Yadav and I am pursuing my Masters in Environmental Science and I am also studying in CUH and I am basically from Rajasthan. Thank you.
Good afternoon everyone, my name is Jyoti. I am research scholar in Department of Microbiology from Central University of Haryana.
Good evening, all of you. My name is Vikas Kumar, a PhD scholar from Environmental Science. I belong to Haryana.
A very good afternoon, everyone. My name is Jyotsna and I am from Haryana. And I am a PhD scholar in the Department of Environmental Science in this university, Central University of Haryana.
Hello, everyone. I am Rohit. I am from Charkhi-Dadri, Haryana, and I am pursuing my PhD from Central University of Haryana in Department of Microbiology.
Good evening, myself Gyan Pratap. I am from Jawaharlal Nehru University.
pursuing environmental science MSc second year student. Basically, I am from Balia, UP.
Hi, I am Prakriti. I'm from Himachal, Shimla, and I'm pursuing PhD in Department of Microbiology. Thank you.
We have people from diverse parts of India, and from few of the institutes like Central University Punjab, Jammu and Karnataka also we have one faculty participant. So it's a good opportunity. That is advantage of having offline programs. You interact with each other. You will have one or two connection in each of the universities from where participants are coming. So because this is not a very tightly packed schedule, so you will have time to interact with each other and get to know each other. And the traditional lignocellulosic biomass ethanol production and maybe biodiesel production, that we have many experts in India. So you can learn, you can attend some other training program, you can discuss with your teachers, but we have very few LCA experts in India. Okay, so that's why we are organizing this program. Try to have some cues from our expert, because LCA will vary depending on area, depending on the crop, depending on the process which you are using. So you have ample opportunity. The same principles will apply for each and every process. You have to just understand the process, and then you have to utilize that that data set for analysis of any life cycle of any process. So make best use of Professor Youngmere, who is here for next 4 more days, and you can just talk to him. You can catch hold of him in guest house also after prior appointment. Okay, maybe during the dinner walk, or maybe you can join him for morning walk. Okay, just take him around the campus and try to extract as much as possible from him, learn from him. It's a rare opportunity to have the senior people. The first thing, they are not coming for 5-7 days to engage in these academic activities, but we are fortunate and we are really thankful to our guest faculty for giving consent and making it to that to Mahendergarh. Many people, they are afraid of coming to Mahendergarh from Delhi even. Okay, but he has come from Austria, so it's a great and so kind of you. And really we look forward to have very fruitful sessions in next coming 4 days. So thank you. So I think tea is coming. We will have tea and